Most of us think that escaping a galaxy is just a matter of time. You just pick a direction, point your starship, and fly in a straight line for a billion years or so. But what if I told you that you could be moving at a speed that defies imagination, fast enough to circle our entire planet in a single second and still be a prisoner of the Milky Way? Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. This isn't a problem of distance. It's a problem of physics. We tend to see space as a long, straight road. But that's not how the universe works. Escaping a galaxy isn't about how far you travel, it's about how fast you go. It's a fight not against empty space, but against an invisible force that holds 100 billion stars in its grip. So, what does it really take to break free? What is the price of freedom from the only home our species has ever known? The answer is far more extreme, and way more fascinating, than you think. The intuitive trap. Why we get it wrong. Our whole lives are built on a simple idea of travel. To get from your house to the store, you cover the distance. To get from one continent to another, you cross the miles between them. It's always point A to point B. We're so used to this that we naturally apply it to everything, even the cosmos. Think about it like being on an infinitely long highway. You get in your car, hit the gas, and just drive. As long as you keep going, you're always getting further from where you started. That's how we picture space travel, right? We're in a cosmic car on a cosmic highway, and the edge of the galaxy is just a very, very distant exit. If we just keep the pedal down for a few million years, we have to get there eventually. But that's the trap. It's a misunderstanding born from our life on Earth, where the biggest force we fight over long distances is friction. In the vacuum of space, a far more powerful force rules everything: gravity. And gravity doesn't care how far you've gone. It cares about your energy. It cares about your speed. To really get it, we have to stop thinking about a journey and start thinking about being. Bound versus unbound. Picture a dog on a ridiculously long leash, tied to a stake. The dog can run for miles, building up incredible speed, feeling totally free. But no matter how far it gets, that leash is still there. Unless the dog runs fast enough to snap the leash, it will always be tied to that stake. It can run to the very end of its tether, but eventually, the leash will pull it back. It can never truly escape. Our solar system is that dog. The galaxy's immense gravity is that leash. We can be hurtling through the void at a staggering velocity, but if that speed isn't enough to break the gravitational leash, we're not escaping. We're just running around inside a really, really big prison cell. So the question isn't, how long does it take to get out of the galaxy? The real question is, how fast do you have to go to snap the leash? This changes the problem completely. It's no longer about crossing a finish line 100,000 light years away. It's about achieving a very specific, violent burst of speed, right here, to overcome a force that has been steering stars for 13 billion years. This is the idea of escape velocity. And it's the first key to understanding why leaving our galaxy is so brutally difficult. The cosmic handcuffs. Introducing gravity and escape velocity. So what is this invisible leash? It's gravity. We feel it every day holding us to the ground, but that's its gentlest touch. On a cosmic scale, gravity is the architect of the universe. It sculpts stars, choreographs the dance of galaxies, and binds everything together. Einstein described it as a curve in the fabric of spacetime itself. Massive objects create dips, or gravity wells, and other things just follow those curves. Imagine a heavy bowling ball in the middle of a big, stretched-out rubber sheet. The sheet sags under its weight. Now, roll a marble across it. If the marble is far from the bowling ball, it rolls in a pretty straight line. But if it gets too close, it gets caught in the curve and starts circling the bowling ball, trapped in an orbit. To get that marble to fly off the sheet entirely, you can't just roll it slowly. It would circle forever. You have to give it a burst of speed, enough momentum to climb up and out of that curve. That critical speed, the minimum speed needed to break free, is called escape velocity. This isn't just a theory, it's a hard number that runs the cosmos. Let's start small. If you throw a ball in the air, it comes back down. But what if you could throw it at 11.2 kilometers per second? That's over 40,000 kilometers per hour. At that speed, it would never fall back to Earth. It would have enough energy to climb out of Earth's gravity well and sail off into space. That's Earth's escape velocity. Every single rocket we've ever sent to the Moon or Mars had to hit that speed. Now, let's scale up. Earth is a small marble on that rubber sheet. What about Jupiter? Jupiter is over 300 times more massive, so its gravity well is way deeper. To escape from Jupiter, you'd need to be going at a blistering 59.6 kilometers per second, more than 5 times faster than escaping Earth. The rule is simple: the more mass, the deeper the gravity well, and the higher the escape velocity. The well analogy is a good one. Escaping a planet is like a jump. A small hop gets you out of a shallow hole. A deep well requires a much bigger leap. Earth's well is deep. Jupiter's is a chasm. We've actually done this. The Voyager probes, launched in the 70s, have escaped the Sun's direct gravitational pull and are now drifting in interstellar space. So, it seems possible, right? Just build a bigger rocket, make a bigger jump. But this is where our human sense of scale completely breaks down. We're not just trying to jump out of a well. We're trying to jump out of a well that's inside another, much, much deeper well. Our solar system is just one little dimple inside the gargantuan depression in space-time created by the entire Milky Way galaxy. And this galactic well is deeper than we can really wrap our heads around. It's a gravity well 100,000 light-years across, and its depth is set by the combined mass of hundreds of billions of stars, gas, dust, and something else entirely. The question then becomes terrifyingly simple: how powerful of a jump do you need to escape that? The unfathomable wall. The Milky Way's escape velocity. Okay, so we have a number for Earth, 11.2 kilometers per second. We see the pattern. More mass means more speed. So, what's the number for the Milky Way? What is the speed you need to hit to finally snap that leash and drift into the true void between galaxies? Before I give you the number, I want you to really try to prepare for it. Think about the fastest thing humanity has ever built, the Parker Solar Probe. By dive-bombing the Sun, it has reached speeds of around 176 kilometers per second. That's over 630,000 kilometers per hour. An incredible, mind-boggling speed. And it's not even close to being enough. Astronomers, using data from instruments like the Gaia satellite, have calculated the Milky Way's escape velocity from our neighborhood. They do this by watching the fastest moving stars in our galaxy, called hypervelocity stars, to figure out the minimum speed needed to be on a one-way trip out. The number they came to is approximately 550 kilometers per second. Let that sink in. 550 kilometers. Every single second. That's nearly 2 million kilometers per hour. At that speed, you could circle the entire Earth in just over a minute. Let's put that in perspective. Escaping Earth is 11.2 kilometers per second. Escaping the galaxy is 550 kilometers per second. It's about * 49 times harder * to leave the galaxy than it is to leave our own planet. That's the difference between hopping over a puddle and jumping over a mountain range. Our fastest spacecraft, The Parker Solar Probe is only hitting about a third of the required speed, and that's only by falling towards the Sun. The Voyager 1 probe, famous for leaving our solar system, is traveling at a relatively pokey 17 kilometers per second. It has escaped the Sun, but it's moving at only 3% of the speed needed to escape the galaxy. It is, and will forever remain, a prisoner of the Milky Way. It will orbit the galactic center for billions of years, a tiny message in a bottle that never even made it out of the harbor. The existence of those hypervelocity stars proves this speed is possible in nature. And by tracing their paths backward, we've found the violent mechanism that can do it. Usually, it involves a pair of stars orbiting each other that wanders too close to the supermassive black hole at our galaxy's center. In a cruel game of cosmic musical chairs, the black hole grabs one star and violently ejects the other one, flinging it away at speeds that can exceed 1,000 kilometers per second. These stars are the lucky few, the ones granted parole. But the price of their freedom was a gravitational encounter of unimaginable violence. For us, without a 4 million solar mass black hole to give us a kick, the challenge is all about propulsion. The energy required to accelerate a ship to 550 kilometers per second is so far beyond our current technology, it's not even on the roadmap. That number is an unscalable wall. It's the clearest, most brutal statement of how tightly this galaxy holds us. The galactic anchor. Why is it so high? But why? Why is that number so insanely high? Why is the galaxy's grip so impossibly strong? The answer, as always, comes down to one thing: mass. The more mass you're trying to escape, the higher the escape velocity. To understand the galaxy's escape velocity, you have to grapple with the galaxy's mass. So, how much does the Milky Way weigh? The number is so big it's almost meaningless, but let's try. By measuring the orbits of stars and star clusters, astronomers have estimated the total mass of our galaxy. The most comprehensive estimates put the mass of the Milky Way at somewhere around 1.5 trillion times the mass of our Sun. That's a 1.5 with 12 zeros after it. That's the weight of the anchor we are chained to. But here's where the story gets really weird. When we look up at the sky, we see the stars, the gas, the dust. If we add up the mass of everything we can see, we don't even come close to 1.5 trillion solar masses. In fact, all the visible matter in our galaxy only accounts for about 15% of its total mass. So where's the other 85%? The answer is, we have no idea. We call it dark matter. This isn't just a placeholder name. It's a statement about the profound weirdness of our universe. Dark matter isn't just dark, like it doesn't shine, it seems to be completely invisible. It doesn't emit, absorb, or reflect any kind of light. It flows through you, through the Earth, through the entire galaxy, as if none of us were even here. So how do we know it exists? We see its shadow. We see its gravity. The first big clue came from watching how our galaxy rotates. In our solar system, Mercury zips around the Sun way faster than Neptune. That's because most of the mass is in the center of the Sun. As you get further out, gravity gets weaker, and things move slower. Astronomers expected to see the same thing in the galaxy. Stars near the center should move fast, and stars on the outer edges should move slow. But that's not what they found. The stars on the outskirts of the galaxy were moving way too fast. So fast, that if the only gravity came from the stuff we can see, they should have been flung off into intergalactic space ages ago. The only way the galaxy can hold itself together is if there's a massive, invisible halo of extra mass surrounding it, holding those fast-moving stars in its grip. That's dark matter. Our galaxy isn't just a pretty spiral of stars. It's a spiral of stars embedded in a colossal, spherical cloud of an invisible substance that outweighs us 6 to 1. This changes everything. When we talk about escaping the Milky Way, we're not just fighting the gravity of the stars we see. We are fighting the gravitational pull of a vast, mysterious halo whose nature is one of the biggest unsolved problems in science. That 550 kilometers per second escape velocity isn't set by the billions of glittering stars. It's dictated by the immense, invisible weight of dark matter. We are prisoners of a ghost. The final boss, the expanding universe. Okay, let's pretend. Imagine we did it. We built a ship that can hit 551 kilometers per second, just over the escape velocity. We point it straight up out of the galactic disk and hit the gas. The ship fights against the pull of 1.5 trillion suns, slowing down as it climbs out of the gravity well, just like a ball thrown in the air. But because we had just enough speed, it never quite stops. Millions of years later, it finally coasts over the edge, free. We've escaped the Milky Way. We won, right? Not exactly. We've just beaten the first boss. Now we face the final one, the universe itself. While we were busy fighting our galaxy's gravity, the entire universe was expanding around us. This isn't galaxies flying through space, it's the fabric of space itself that is stretching. The classic analogy is dots on a balloon. As you inflate the balloon, the distance between every dot and every other dot grows, because the rubber itself is expanding. This expansion creates a whole new problem. On local scales, gravity is strong enough to win. The stars in the Milky Way aren't flying away from each other. The same is true for our immediate neighborhood, a cluster of galaxies called the local group. In fact, the Milky Way and our big neighbor, Andromeda, are actually being pulled toward each other by gravity and are on a collision course. So, by escaping the Milky Way, we haven't become a true cosmic explorer. We've just graduated from being a prisoner of our galaxy to being a prisoner of our local group. We can now wander the yard between the Milky Way, Andromeda, and their smaller satellite galaxies, but we're still inside a bigger prison. To truly travel to other galaxy clusters, you'd need to achieve the escape velocity of the asterisk entire local group, an even more monumental task. But there's an even more fundamental limit. Because the universe's expansion is accelerating, there's a cosmic event horizon about 16 billion light-years away beyond which everything is receding from us faster than the speed of light. This doesn't break Einstein's rules, because it's space itself stretching. But it means that any galaxy beyond that horizon is lost to us forever. Light leaving it now will never reach us. A ship leaving here now, even one traveling at the speed of light, could never, ever get there. The space between us and them is expanding too fast to cross. This is the ultimate prison. We're bound by our galaxy's gravity, then by our local group's gravity, and finally, we're confined to a finite bubble of the universe by the expansion of spacetime itself. The vast majority of the cosmos is, and will forever be, completely out of reach. The beautiful prison. So, it seems we're trapped. Trapped by a speed limit we can't break, held by the gravity of an invisible substance, and confined to our cosmic neighborhood by the stretching of spacetime itself. It sounds bleak, a story of cosmic confinement. But maybe that's the wrong way to look at it. The difficulty of escaping the Milky Way isn't a sign of our weakness, it's a testament to the galaxy's grandeur.
We are bound by the collective gravity of trillions of suns and a mysterious halo that defines our entire cosmic environment. The chains that hold us are forged from stardust and the biggest mysteries of the universe. And besides, to feel imprisoned by the galaxy is to misunderstand our place in it. We aren't separate from the Milky Way. We are the Milky Way. Every atom in our bodies, every element heavier than hydrogen, was cooked in the heart of a star that lived and died right here, in this galaxy. The iron in your blood, the calcium in your bones, it's all recycled stardust. We are the galaxy, having a brief, conscious experience. The fact that our home is so hard to leave is exactly what makes it a home. Its immense gravity is what holds the stars in their majestic, swirling arms. It's what gathered the gas and dust that allowed our sun, our planet, and us to form in the first place. We exist because this prison is so effective. So when you look up at that milky band of light across the night sky, don't see the walls of a jail. See the architecture of your home. See the immense scale not as a barrier, but as a measure of the magnificent structure you are a part of. You are not just living in the universe, you're the universe's way of looking at itself. And for now, for this brilliant moment in cosmic history, this is where we get to do it. We are home. Part 2. Why galaxies hold things together so well. A galaxy can look strangely delicate from far away. When we see one in a photograph, it often appears soft. A pale spiral of light suspended in blackness. A quiet swirl. Something almost decorative. It can feel less like a physical structure and more like a brushstroke across the dark. But that first impression is deeply misleading. A galaxy is not a fragile cloud that just happens to be drifting in one shape for a little while. It is not a loose gathering of stars wandering in the same neighborhood by accident. It is a vast gravitational system, one of the most stable and persistent structures in the universe. And if we want to understand why escaping a galaxy is so difficult, we first have to understand why a galaxy holds on so well in the first place. Because that is the real secret. Before anything can escape, something has to be strong enough to keep it. If you enjoy these slow journeys through the universe, you can always leave a quiet like, subscribe if you'd like to stay a little longer, and share where you're listening from tonight. There is something oddly comforting about imagining all these distant structures while someone, somewhere, is listening from a bedroom, a city apartment, a quiet road, or the edge of a sleeping town. Now, when most people picture a galaxy, they imagine stars scattered through space, like glitter tossed into the air. And that image is understandable. A galaxy contains so much empty space that it is difficult for the mind to hold the scale together. The distance between stars is so enormous that everything can begin to seem disconnected. But a galaxy is not really a scattering. It is more like a long, slow agreement. An agreement between mass and motion, between speed and gravity, between the urge of matter to continue moving and the quiet pull that keeps bending that motion inward, again and again, over millions and billions of years. That is what makes a galaxy feel so strange. Everything inside it is moving, yet the whole structure persists. Stars race through the galactic disk at astonishing speed. Gas drifts, compresses, and collapses into new stars. Star clusters orbit. Dust spreads into great dark lanes. Even our own sun is traveling through the Milky Way at a speed far beyond anything we experience in daily life, and yet the galaxy itself does not simply fly apart. It holds. And it holds because gravity, when given enough mass, becomes patient and immense. On Earth, gravity feels local. It pulls an apple down. It keeps our feet on the ground. It makes rain fall and rivers run downhill. We are used to thinking of gravity as a small, familiar background force. But on the scale of a galaxy, gravity stops feeling ordinary. It becomes architecture. It becomes the thing that gives the whole structure shape. A helpful way to picture this is to imagine a wide, shallow valley. Now imagine thousands, then millions, then billions of tiny objects moving within it. None of them are nailed into place. None of them are frozen. They are all moving freely, and yet they remain part of the same landscape because the shape of the valley guides their motion. A galaxy is something like that, though far more elegant and far more extreme. Stars are not hanging still inside a galaxy like ornaments in a glass case. They are moving along paths shaped by the combined gravity of everything else. That is the important part. Not just the gravity of one central object, though galactic centers can be powerful. Not just the gravity of a nearby star cluster, but the total gravitational influence of the galaxy as a whole. This is one of the easiest places for intuition to go wrong. We often imagine that galaxies are held together because everything is simply falling toward the center. But that is only part of the picture, and not the most useful one. Stars are not normally plunging straight inward like stones dropped into a well. They are moving sideways, around the galaxy, with enough speed to keep missing the center over and over again. That repeated missing is what we call orbit. And orbit is one of the universe's quietest miracles. A star in orbit is always falling, but never arriving. It is being pulled inward by gravity, while its own motion carries it forward. The result is a long, continuous curve through space. On a small scale, we see this with moons around planets and planets around stars. On a galactic scale, we see the same principle expanded into something breathtakingly large. Our Sun, for example, does not sit still in the Milky Way. It is traveling around the galactic center, and it has been doing so for a very long time. One full circuit takes hundreds of millions of years, which means that since the dinosaurs vanished from Earth, our solar system has not even completed one full orbit around the galaxy. That is the kind of timescale we are dealing with. So when we ask why galaxies hold things together so well, one answer is this: they do not hold things by stillness. They hold things by motion that remains bound. And that is a very different kind of holding. It is more like a dancer staying within the shape of a dance than a stone being locked in a box. It is more like a train following invisible rails than a bird trapped in a cage. Everything is moving, but not freely enough to leave. That distinction matters, because it explains why a galaxy can seem both dynamic and stable at the same time. The stars move. The structure endures. The system changes. The whole remains. If you were somehow far above the Milky Way, watching over a stretch of time far longer than a human life, you would not see a frozen pattern. You would see an immense rotating system, almost like weather on a scale beyond imagination. You would see stars tracing paths, clouds of gas shifting, new stars igniting, old stars fading. And still, through all of it, the galaxy would remain recognizably itself. That persistence is not accidental. It comes from mass. A galaxy contains an astonishing amount of it. Hundreds of billions of stars, vast clouds of hydrogen and dust, dense star clusters, stellar remnants, black holes, and more. And while any one star pulls only modestly on distant objects, the combined gravity of a galaxy becomes overwhelming. A single voice might be quiet. A choir can fill a cathedral. Gravity works like that. Every contribution adds to the whole. And once enough mass gathers into one region of space, it begins to create a deep gravitational environment that is hard to escape. That environment is what keeps a galaxy together. You can think of it as a kind of invisible basin. Not a solid wall, not a shell, not a boundary you could point to with your hand, but a region where motion is continuously curved back into membership. A star inside that basin may travel for millions of years and still remain part of the same galactic story. This is why distance alone is so misleading. Something can be very far from the galactic center and still be held. It can be moving incredibly fast and still be held. It can live its entire existence far out in the galactic suburbs, so to speak, and never come close to freedom. Because holding is not about closeness. It is about whether the total energy of motion is enough to break loose. And most of the time, it is not. That is why stars do not simply drift away. From a human point of view, it can seem natural to imagine that if enough time passes, things should slowly scatter. That is how many systems on Earth behave. A crowd spreads out. Smoke disperses. A spilled glass of water runs across the floor until it loses form. We assume that if something is not tied down, it should eventually unravel. But galaxies are not like spilled water. They are not random arrangements waiting to dissolve. They are self-gravitating systems, which means the very thing inside them that wants to move is the same thing being governed by the mass of the whole. Stars are not separate from the galaxy's holding force. They are part of it. Every star is both passenger and participant. It is being held by the galaxy, and it helps hold the galaxy together in return. There is something beautiful about that. The galaxy is not holding its stars in the way a jailer holds prisoners. It is holding them the way a whirlpool holds water, the way a melody holds notes, the way a story holds its own chapters together. Each part belongs to the structure, and the structure exists because of all the parts. This is also why galaxies can survive for such astonishing lengths of time. Not unchanged, because nothing in the universe is completely unchanged, but coherent. They can endure collisions, tidal interactions, bursts of star formation, the deaths of giant stars, and the slow reshaping of their own inner regions. Yet even through that turbulence, the deeper gravitational identity remains. They stay together because the grip is distributed, not concentrated in one place alone, but spread throughout the system. That matters more than it may seem. Imagine if all the mass of a galaxy were packed only into a tiny central point, with almost nothing elsewhere. The behavior of the outer regions would be very different. But real galaxies are extended systems. Their matter is spread across disks, bulges, halos, and clouds. Their gravitational field is not a single sharp tug. It is a broad, structured landscape. And inside that landscape, stars find paths. Some move in fairly orderly orbits within the disk. Some belong to the central bulge and follow more complex, tilted routes. Some old stars and clusters roam the halo in long, stretched paths far above and below the main galactic plane. But despite all these differences, they remain part of the same bound system. That is the quiet genius of a galaxy. It does not require every star to behave the same way. It only requires that the total motion stays inside the larger gravitational conversation. This is where spiral galaxies like the Milky Way become especially fascinating. Those graceful spiral arms can make it look as if the galaxy is a rigid pinwheel, turning like a toy. But that is not really what is happening. The arms are not solid blades. They are better thought of as regions of greater density, places where stars and gas crowd together more strongly for a time as they orbit. In other words, the galaxy is not a machine made of rigid parts. It is more like traffic flowing through patterns. Cars move. The traffic jam shape persists. Stars move. The spiral pattern remains. That means the galaxy's stability is not the stability of stillness. It is the stability of organized motion. And that kind of stability can be surprisingly strong. It also explains why gas and dust matter so much. A galaxy is not only a collection of old stars keeping to themselves. It is also a place where material gathers, cools, collapses, and creates new stars. Great molecular clouds drift through the disk. Spiral arms compress gas. Gravity builds denser pockets. New stars are born. Some live quietly for billions of years. Others burn hot and die young, exploding and sending heavy elements back into the galactic medium. So the galaxy is not just holding stars. It is holding the conditions for renewal. It holds the raw material from which future stars can emerge. It holds the matter that one day becomes planets. It holds the elements that eventually become oceans, mountains, trees, blood, bone, and thought. That is another reason galaxies are such powerful structures. They are not merely gravitational containers. They are long-lived environments where complexity has time to happen. Without that holding power, everything would be much more chaotic. Gas would not gather in the same way. Star formation would become far less structured. Planetary systems like our own might be harder to build or harder to preserve. The conditions that allow stable skies, long chemistry, and slow biological history would be much rarer. In a very real sense, the fact that galaxies hold themselves together so well is one of the reasons beings like us can exist to wonder about them. And yet, even now, we still have not reached the deepest part of the story. Because if you add up only the mass we can easily see in many galaxies, something does not quite fit. The outer stars often move in ways that suggest there is more gravity present than visible matter alone can explain. As if the galaxy has extra weight hidden in darkness. As if the luminous spiral is only the bright center of a much larger structure. We will come back to that mystery later, because it deserves its own quiet attention. For now, it is enough to say this: galaxies seem to be even better at holding themselves together than the visible stars alone would predict. And that should tell you just how serious this problem of escape really is. Because when you picture leaving a galaxy, you are not leaving a loose cloud. You are not slipping away from some casual arrangement of stars. You are trying to break free from one of the deepest, most persistent gravitational structures nature knows how to build. A structure large enough to carry hundreds of billions of suns. Gentle enough, from a distance, to look like a swirl of dust. Powerful enough, from within, to keep whole star systems bound for ages longer than civilizations, longer than species, longer than most worlds ever remain habitable. That contrast is part of what makes galaxies feel so haunting. They are beautiful because they are ordered. And they are ordered because gravity is relentless. When you look up into the night sky and see the faint river of the Milky Way stretching above the Earth, it can feel light and almost airy. A silver mist. A quiet band of stars. But that softness is an illusion of distance. What you are really looking at is the inside of an enormous gravitational home, a system so large and so stable that our sun has been moving within it for all of human history without ever coming close to the edge of freedom. We are not near the boundary. We are deep inside the hold. And maybe that is worth pausing on for a moment, because it changes the emotional meaning of the subject. To say that a galaxy holds things together well is not only to say that escape is hard. It is also to say that belonging, on a cosmic scale, is powerful. Our world is not floating alone in random emptiness. It is embedded in a structure with shape, rhythm, memory, and weight. The stars above us are not merely scattered lights. They are neighbors inside the same vast gravitational city. The same force that makes escape difficult is also the force that allowed our corner of the universe to become stable enough for stars like the Sun to shine quietly for billions of years. In that sense, the galaxy's grip is not just a barrier. It is also a shelter. It is the reason the Milky Way can be a home at all. And once you start to feel that, the next question becomes even more interesting. If a galaxy is this good at holding onto its stars, then why don't those stars simply slow down and fall inward? Why do they keep tracing those long paths instead of collapsing into the center? Why do they remain in motion at all? That is where the story naturally leads next. Because the strength of the grip is only half the answer. The other half is the dance. Part 3: How gravity works on a galactic scale. If you could somehow step outside the Milky Way and look back at it from a safe distance, one of the first things you might notice is how calm it appears. Not empty, and not still, but calm. A spiral galaxy from far away has a strange kind of grace to it. The arms seem to open gently from the center. The light looks soft. The whole structure appears balanced, almost delicate, as if it were floating in perfect silence without effort. And yet that appearance hides something immense. Because a galaxy is not calm in the way a sleeping room is calm. It is calm in the way an ocean can look calm from high above, even while powerful currents are moving beneath the surface. That is what we are really dealing with here. A galaxy is full of motion, full of mass, full of invisible structure. And the force shaping all of it, guiding all of it, and holding all of it together is gravity. But not gravity in the simple everyday way we usually think about it. Not just the force that drops a pen from your hand or keeps your feet on the ground. Galactic gravity is something larger, slower, and harder for the human mind to picture. It works across distances so vast that ordinary intuition begins to fail. It does not shout. It does not flash. It simply keeps acting, year after year, million after million, quietly bending the paths of stars until entire cosmic systems begin to look stable, almost eternal. And if we want to understand why escaping a galaxy is so difficult, then sooner or later we have to slow down and really sit with that force. We have to understand what gravity is doing, not just near a planet or a star, but across the full width of a galaxy. Because once you see that clearly, the whole problem changes. It no longer feels like a question of travel alone. It becomes a question of living inside a structure so massive that motion itself is constantly being curved back into belonging. If you enjoy drifting through these slow cosmic ideas before sleep, you can leave a quiet like, subscribe if you'd like more of these gentle journeys, and share where in the world you're listening from tonight. It is always a little comforting to imagine these thoughts moving softly through different rooms, different cities, different nights, while the universe remains above all of them. Now, to begin, it helps to forget the word gravity for a moment and think instead about behavior. What does gravity actually do? At the most basic level, gravity causes matter to attract matter. Anything with mass pulls on anything else with mass. A grain of sand pulls on a mountain. A person pulls on the moon. The moon pulls on the earth. The earth pulls on the sun. The sun pulls on the stars around it. Usually these tiny attractions are too small to notice in daily life. But once enough mass gathers together, gravity stops feeling small. It starts to shape the entire environment. That is the first important idea. Gravity is weak when compared to some other forces in physics, but it has two enormous advantages. First, it never seems to switch off. And second, it always adds up. If you gather more matter, you get more gravity. Keep gathering matter, and the effect becomes enormous. That is why galaxies are such powerful places. They contain so much mass that gravity is no longer just one influence among many. It becomes the ruling background condition. It becomes the thing that decides where stars travel, how gas moves, where structures form, and how difficult freedom really is. On Earth, you can escape local gravity with enough speed. That is already a tremendous challenge, but at least the system is simple enough to imagine. A planet is a fairly compact object. You move away from it, and its pull drops off. The farther you go, the easier the escape becomes. A galaxy is different. A galaxy is not a single compact object sitting neatly in one place. It is a huge distribution of mass spread across tens of thousands of light years. Stars are scattered through the disk. Gas floats in clouds. Old star clusters move through the halo. Dense regions sit closer to the center. Other matter extends far beyond the bright visible parts. So when you move through a galaxy, you are not merely leaving one object behind. You are traveling through an entire gravitational landscape. That is why the scale matters so much. When people first start thinking about galaxies, it is very natural to picture the center as doing almost all the work. There is a bright bulge in the middle, maybe a supermassive black hole there too, and it feels intuitive to imagine everything else simply circling that central anchor. But real galaxies are more subtle than that. The center matters, of course. It is massive and influential. But much of the galaxy's gravitational structure comes from the total spread of matter throughout the whole system. In other words, a galaxy is not held together by one hand at the center alone. It is held together by the combined pull of everything. That can be a little difficult to picture, so it helps to think of something simpler first. Imagine standing in a valley. The shape of the land around you determines where a rolling ball will go. If the valley is steep, the ball moves differently than if it is shallow. If the ground is uneven, the path changes again. The ball is not responding to one point only. It is responding to the shape of the entire landscape. Gravity in a galaxy works a bit like that. Stars move through a gravitational terrain created by all the mass around them. That terrain is not visible in the ordinary sense. You cannot look out and see glowing lines marking where the slopes are steepest. But the stars feel it. Gas feels it. Even the overall structure of the galaxy reflects it. And this is where the idea of orbit becomes much deeper than it first seems. An orbit is often described as an object falling around something rather than straight into it. That is true, But in a galaxy the story is broader. A star is not just falling toward one object. It is moving through a distributed field, a kind of invisible topography formed by countless masses acting together. Its path curves because space-time, to use Einstein's language, is shaped by the matter in that region. Or, if you prefer the simpler older picture, the star curves because the total gravity of the galaxy keeps redirecting its motion. Either way, the result is the same. Motion that might have continued in a straight line gets bent. Again and again, it gets bent. That repeated bending is the essence of what gravity does on a galactic scale. A star would not naturally choose a circular path. Left alone, matter tends to keep moving in a straight line. That is one of the deepest rules in physics. So if a star is going around the galaxy instead of flying away into the dark, that means something is constantly changing its direction. Not stopping it, not freezing it, but curving it. And the force doing that curving is gravity. This is why a galaxy can feel so stable even though everything inside it is moving. The stability is not the absence of motion. It is motion under continuous guidance. That is a very important distinction, and it is one the mind does not always make easily, because in ordinary life stable things usually look still. A parked car is stable because it is not moving. A building is stable because it is not moving. A glass on the table is stable because it stays where it is. But a galaxy belongs to a different category of order. A galaxy is stable the way a hurricane is stable for a time, or the way a whirlpool is stable. Its parts are in motion, yet the overall structure persists because there is a deeper pattern shaping that motion. In a galaxy, gravity is that pattern. The sun is a perfect example. Our sun is not sitting quietly in one place while the galaxy turns around it. It is racing around the Milky Way at extraordinary speed. And so is the Earth with it. And every person who has ever lived has spent their entire life moving through the galaxy without feeling it. We feel the Earth spin. We orbit the sun. And all the while, the whole solar system is also traveling through the wider gravitational design of the Milky Way. That is one reason galactic gravity is so hard to intuit. We are inside it. We are participating in it. We have never known life outside it. So it feels normal, even though the scale is almost absurd. To get a better sense of this, think about the time involved. A human life is short enough that the sky seems basically unchanged. The stars rise and set, the constellations return, the Milky Way arches across dark places much as it did for earlier generations. But that apparent stillness is created by our limited timescale. If you could watch the galaxy over millions of years in the way you might watch weather over an afternoon, you would begin to see the true motion. Stars shifting, clouds drifting, orbits progressing, structures evolving slowly, patiently, with an elegance so gradual that only time itself reveals it. This is one of the gentle deceptions of astronomy. The cosmos looks still because we are brief. In reality, the galaxy is an enormous choreography being shaped by gravity across spans of time that hardly fit inside ordinary language. And because gravity keeps acting through all of that time, its effects accumulate. That is another crucial point. Galactic gravity does not need to be dramatic at every moment to be powerful in the long run. A tiny change in direction, applied continuously over millions or billions of years, is enough to shape the path of a star completely. That is how quiet forces become great architects. A single nudge seems trivial. A trillion nudges become structure. There is also something else that matters here, something that makes galaxies harder to escape than they first appear. Gravity does not only come from what looks bright and obvious. We are naturally drawn to the glowing parts of a galaxy, the crowded starfields, the brilliant central regions, the luminous arms. But light is not the same as mass. Some regions shine brightly, others are dim, and much of the galaxy's gravitational influence comes from material that does not announce itself so clearly to the eye. Some of that is ordinary matter in less visible forms, like cool gas or faint stars. But some of it appears to be something stranger, a hidden mass that extends far beyond the visible disk. We will spend more time with that later. For now, what matters is the result. Galaxies seem to possess deeper gravitational reservoirs than visible light alone would suggest, which means the gravitational terrain is broader, heavier, and more serious than the bright spiral shape might imply. This helps explain one of the more surprising facts about galactic motion. If gravity came only from the visible matter concentrated toward the center, you might expect outer stars to move more slowly in a certain neat way, much like planets farther from the Sun move more slowly in their orbits. And yet when astronomers study galaxies, they often find that stars far out in the disk are still moving unexpectedly fast, as if the galaxy's pull remains stronger at those distances than it ought to, based only on what we can see. That is one of the clues that tells us galactic gravity is not simple. It is richer than first appearances. It extends farther than bright starlight alone would lead us to expect. And because it extends so far, escaping the galaxy is not just about getting beyond the visible arms. It means climbing out of a gravitational environment that keeps going long after the bright scenery begins to thin. This is why the phrase leaving a galaxy can be so misleading. It sounds like crossing a border. It sounds like once you pass a certain region, perhaps the glowing part, then you are free. But gravity does not really draw borders that way. It fades gradually. It stretches outward. It claims space softly rather than sharply. So the real challenge is not touching some outer line. The real challenge is gaining enough energy that the galaxy cannot meaningfully call you back. And that brings us to one of the most beautiful things about gravity on a galactic scale. It creates membership. That may sound like a strange way to describe a force, but it is accurate. If gravity keeps curving your motion so that you remain part of the system, then you belong to that system in a literal physical sense. A star in the disk belongs to the galaxy. A globular cluster in the halo belongs to the galaxy. A gas cloud drifting toward future star formation belongs to the galaxy. Even a small dwarf galaxy orbiting a larger one can exist under its gravitational influence, held in a more distant and complicated form of belonging. When we say something is bound to a galaxy, what we really mean is that its motion and energy are such that the galaxy still has a claim on it. It has not escaped the story. This is why stars do not just head off in random directions, even though space is vast and mostly empty. Their motion is not random because they are not moving through emptiness alone. They are moving through a shaped environment. The emptiness contains structure. The darkness contains guidance. The silence contains force. It is one of the quietest truths in astronomy. Space can look empty and still be full of consequence. And once you begin to feel that, many other things start to make more sense. The spiral arms, for instance, are not merely decorative features painted onto the galaxy. Their existence reflects the way matter responds to gravity, density, and motion together. Gas drifts into denser regions. Stars pass through. Patterns emerge and endure. Not rigidly, not forever, but long enough to give the galaxy its familiar beauty. The central bulge, too, speaks of gravity's long work. It is crowded because mass has collected and remained important there over immense time. The halo of old stars and clusters tells a related story, one of ancient motions and deep gravitational history. Even the fact that galaxies can merge, distort, and yet continue as recognizable systems reminds us how powerful gravity is on these scales. It does not merely hold isolated objects. It mediates relationships between whole galactic structures. And yet for all its scale, galactic gravity is still built from the same principle we meet everywhere else in the universe. Mass attracts mass. More mass creates more pull. Motion responds. Paths bend. Structure emerges. The rule is simple. The consequences are enormous. Perhaps that is one of the reasons gravity feels so profound. It does not need to be complicated to produce grandeur. With enough matter and enough time, it can turn simple attraction into suns, solar systems, galaxies, galaxy clusters, and the vast architecture of the observable universe. It is one of the great slow makers of reality. And slowness matters here. Because to really understand a galaxy, you have to think in long durations. Gravity does some of its finest work over spans of time so extended that human concern almost disappears inside them. It builds order gradually. It stabilizes motion gradually. It allows stars to orbit for ages, gas to gather, structures to settle, and systems to remain coherent across billions of years. When we see a galaxy shining in the dark, we are seeing the current shape of a very long conversation between matter and gravity. A conversation still unfolding. A conversation our own solar system has been part of for a very long time. And from inside that conversation, escape becomes much harder to imagine in a casual way. Because now we are no longer picturing a traveler leaving a place. We are picturing an object trying to overcome the full curvature of a vast gravitational environment, one created by a whole galaxy's worth of mass acting across unimaginable distances. That is not a small problem. It is not even a problem that begins at the edge. It begins everywhere inside the system, because everywhere inside the system gravity is already at work. The Milky Way is not simply around us. It is acting on us. It is shaping the motion of everything in our neighborhood, including the sun, including the planets, including us. And yet there is something deeply calming in that thought too. Because the same force that makes escape difficult is also the force that gives the galaxy continuity. It is the reason the night sky is not pure chaos. It is the reason stars can remain in long relationships with the larger structure. It is the reason our solar system has had the stable galactic home needed for long stretches of planetary history to unfold. Gravity binds, yes, but it also preserves. It keeps a place from becoming only debris. It gives the galaxy memory. By now, you can probably feel the next question quietly forming. If gravity is constantly pulling inward on all these stars, if it is always curving their motion, why do they not simply lose the argument and fall into the center? Why does the galaxy not collapse into one crowded blaze of matter? Why do stars keep their distance and continue tracing those long paths instead of plunging inward? That is where the mystery becomes even more beautiful. Because gravity may provide the pull, but motion provides the balance. And the stars, for all their obedience to gravity, are not passive. They are moving fast enough to keep missing the center, over and over again, for ages. That is the next part of the story. It is the reason galaxies do not just hold things. It is the reason they can hold them in motion. Part 4. Why stars do not simply drift away. If gravity is always pulling inward, then a very natural question begins to appear. Why do stars not simply fall? Why does a galaxy not collapse into its own center, with every star rushing inward until the whole thing becomes one crowded blaze of light? Or, from the other direction, why do stars not slowly wander off into the dark? Why do they not loosen their grip on the galaxy, drift apart over time, and vanish into intergalactic space one by one? When people first imagine a galaxy, they often picture something caught between those two fates. Either everything should fall inward, or everything should drift outward. Either collapse, or unravel. Because in ordinary life, things tend to behave that way. A dropped object falls. A scattered cloud disperses. A pile of sand slides downhill. We are used to systems breaking apart or sinking toward a resting place. But galaxies are not built like piles of sand. They are built from motion. And that changes everything. The reason stars do not simply drift away is not that they are nailed into place. It is not that some invisible barrier surrounds the galaxy like a glass dome. And it is not that the stars are standing still, waiting to be held. In truth, the stars are moving constantly, and often at astonishing speed. What keeps them from escaping is not stillness. It is the very particular relationship between their motion and the gravity of the galaxy around them. That relationship is what creates orbit. And orbit, once you really sit with it, is one of the strangest and most beautiful ideas in the universe. If you enjoy these slow cosmic stories before sleep, you can gently like the video, subscribe if you want more calm journeys like this, and leave a quiet comment about where you are listening from tonight. It is always comforting to imagine these thoughts moving through so many different nights at once. Now, when people hear the word orbit, they usually think of something neat and simple. A planet going around a star, a moon going around a planet, a clean circle, a repeated path, something orderly and familiar. But orbit is a little more mysterious than that. At its heart, orbit is not about an object being tied to another object. It is about an object moving fast enough sideways that, although gravity keeps pulling it inward, it keeps missing the place it would otherwise fall into. That is the key idea. A star does not stay in the galaxy because it is motionless. A star stays in the galaxy because it is falling in a curve. Imagine standing on a high mountain and throwing a stone. If you throw it gently, it falls nearby. If you throw it harder, it travels farther before hitting the ground. Throw it harder still, and it goes even farther. Now imagine a world without air resistance and with enough open space. If you could throw that stone fast enough, the surface of the Earth would curve away beneath it at the same rate that it falls. The stone would keep falling, but it would never hit the ground. It would be in orbit. That old thought experiment is often used for satellites around Earth, but the same principle extends upward through the entire universe. The moon is always falling toward Earth, but its sideways motion keeps carrying it onward. The Earth is always falling toward the sun, but its forward motion keeps it in a long, graceful path. And our sun, along with the whole solar system, is always falling within the Milky Way, while its galactic motion keeps it from plunging into the center. This means that stars do not simply drift away because most of them are not drifting in the first place. They are moving within a pattern. Their paths are being bent continuously by gravity, and as long as their speed and direction remain within a certain range, they stay bound to the galaxy. That bound motion is what makes a galaxy possible. Without it, the stars would not form a long-lived system. They would either collapse inward too quickly or disperse into emptiness. What we call a galaxy is really the quiet balance between those two extremes. Too little sideways motion, and a star drops deeper inward. Too much, and it can break free. But in between those extremes lies the long, stable middle ground where most stars live out their lives. That middle ground is where galaxies breathe. And that is where our sun has spent all of its existence. It is worth pausing here, because this is one of those places where the human mind can feel a little disoriented. We are used to thinking of motion and stability as opposites. If something is moving, we expect it to be unstable. If something is stable, we expect it to be still. But astronomy teaches something gentler and stranger. A thing can be stable because it is moving. A galaxy holds together not by stopping its stars, but by allowing them to move in ways that remain bound. Stability emerges from motion, not from the absence of it. That is why the night sky can look so calm while the reality behind it is so dynamic. Our sun is not parked inside the Milky Way. It is racing through the galaxy at a speed that, in ordinary human terms, is almost absurd. And yet, because everything around it is also part of the same larger gravitational system, that tremendous speed does not throw it loose. It becomes part of the balance. This is another place where intuition can fail us. On Earth, speed feels like freedom. A fast-moving thing seems harder to contain than a slow one. And in many situations that is true. But in a galaxy, speed alone does not guarantee escape. What matters is whether the speed is enough, in the right direction, to overcome the galaxy's overall gravitational hold. Most stars are moving fast, but not free. That is an important difference. A star may travel hundreds of kilometers every second and still remain deeply bound to the galaxy. It may cover immense distances over millions of years and still never come close to leaving. Because leaving is not about motion in a general sense. It is about having more than enough energy to stop being part of the galaxy's gravitational story. Most stars never do. Instead, they spend their lives tracing paths that keep bringing them back around, again and again, like travelers who never leave the country they were born into, even if they roam far within it. Our own sun is a perfect example of this. It is not near the galactic center. It is not near the outermost edge either. It lives in one region of the Milky Way and moves through the galaxy on a long orbit that takes hundreds of millions of years to complete. That means that the continents on Earth, the animals that rose and vanished, the entire history of human civilization, all of it has unfolded during only a tiny fraction of one galactic orbit. So when we talk about a star not drifting away, we are not talking about a short-term condition. We are talking about a kind of long obedience to gravity, stretched across spans of time so vast that even the history of species begins to look brief. And yet stars do not all move in the same way. This is another beautiful part of the story. A galaxy is not a rigid machine with every part locked into identical motion. Stars in the thin disk move differently from stars in the bulge. Halo stars often follow stranger, more tilted, more elongated paths. Some stars travel in relatively orderly orbits around the center. Others weave in ways that are more complex. Some move through dense spiral regions. Others spend long ages far from the bright, crowded plane of the galaxy. But all of these different motions can still remain bound. That is the real point. To stay in the galaxy, a star does not have to follow one perfect track. It simply has to remain under the galaxy's gravitational claim. Its energy must remain below the level required for escape. As long as that is true, the star may wander through many kinds of paths while still belonging to the larger system. You can think of it like water moving inside a great whirlpool. Not every drop follows the exact same line. Some curve inward more sharply. Some circle farther out. Some shift from one path to another. But the whole structure remains coherent because the motion stays within the larger pattern. Galaxies are like that. They are not still pictures. They are enduring motions. This also helps explain why stars do not simply slow down and fall into the center. Because falling inward is only one possibility, and not the one most stars are set up to do. Their sideways motion matters. Their angular momentum matters. The path they already carry matters. That phrase, angular momentum, may sound technical, but the idea behind it is simple enough. Things in motion tend to keep moving in the way they already are, unless something changes that motion. A spinning skater keeps spinning. A rolling wheel keeps rolling. A planet or star already moving sideways does not just forget that motion because gravity exists. Gravity bends the motion, yes, but it does not erase it. So instead of plunging straight inward, the star keeps moving around. That is why galaxies do not usually collapse into a single bright knot. There is too much motion in the system for that. The stars are not just sitting there waiting to fall. They are already moving through the galaxy with tremendous lateral momentum, and that motion continuously resists direct collapse. In that sense, a galaxy is almost like a compromise. Gravity would like to pull matter inward. Motion would like to continue forward. Orbit is what happens when neither side fully wins. And out of that compromise comes structure. Out of that compromise comes time. Out of that compromise comes the possibility of stable worlds, long-lived stars, and places where life can slowly emerge. There is something almost tender in that. The galaxy does not endure because one force crushes the other. It endures because both remain in conversation. Still, stars are not forever locked into perfectly unchanging paths. Galaxies are real systems, and real systems evolve. Over enormous spans of time, stars can be nudged by nearby encounters, by giant molecular clouds, by the shifting structure of spiral arms, by the gravitational influence of the galactic bar, or by long interactions with clusters and passing companions. Their orbits can change. Their paths can become a little more stretched, a little more tilted, a little more disturbed. But usually these changes do not fling them out. Usually they simply reshape the way the stars remain part of the galaxy. That is another important point. A galaxy is not static, but it is resilient. It can absorb change without losing itself. Stars can migrate inward or outward over time. They can shift to slightly different orbital neighborhoods. They can be stirred, heated, or scattered into more complex paths. Yet the galaxy remains a bound system because the deeper gravitational structure is still there. The stars are not held by perfection. They are held by depth. This is one reason the visible calm of the Milky Way hides so much movement. Underneath the quiet band of starlight we see from Earth lies an endless traffic of motion. Stars crossing the disk, gas clouds turning and colliding, clusters orbiting, old stars wandering the halo. Everything moving, almost nothing escaping. And perhaps that is the most important sentence in this part of the story. Everything is moving, almost nothing is escaping. That is what a galaxy is. A place where speed and confinement exist together. A place where motion does not mean freedom. A place where the stars can race for billions of years and still remain members of the same vast structure. Of course, there are rare exceptions. Now and then, nature does produce stars that really can leave. A violent gravitational interaction can fling a star outward at such extraordinary speed that it becomes unbound. These are sometimes called hypervelocity stars. They are unusual, and their lives tend to involve something dramatic, often a close encounter with the supermassive black hole in the galactic center or another intense gravitational event. Those stars are fascinating because they prove escape is possible in principle. But they are interesting precisely because they are rare. Their rarity tells us something essential. The ordinary life of a star in a galaxy is not escape. It is belonging. To truly break free usually requires something exceptional, something violent, something outside the calm rhythm that defines most galactic motion. That should give us a better feel for just how strong the galaxy's hold really is. If a star, an object already moving at immense speed, usually remains bound for billions of years, then escape is not a casual thing. It is not the natural outcome of wandering long enough. It is not what time alone provides. The stars do not drift away because the galaxy is not loose enough to allow that. Its gravity keeps curving their paths back into participation. Its mass makes the system deep enough to hold them. Its scale makes ordinary motion feel free while remaining trapped. And perhaps there is another reason this subject feels so compelling. It touches something slightly philosophical in us. When we picture the stars, we often imagine solitude. We think of isolated suns suspended in great darkness, each far from the others, each alone in the void. And on one level, that is true. The distances between stars are immense. Space inside a galaxy is mostly emptiness. But the galaxy teaches a softer lesson. Even at enormous distance, things can still belong together. The stars are separated by light years, yet they are part of one gravitational system. They are not close in the ordinary sense, but they are connected in the deeper language of motion and mass. They participate in a shared structure they can never fully see from within. We live inside that structure too. The Earth, the Moon, the Sun, every person who has ever watched the Milky Way rise above a dark horizon, all of us are taking part in the same hidden orbit. We are not outside observers studying a galaxy from afar. We are carried inside it. The stillness of night is happening inside motion so vast we do not feel it. That is one of the great quiet comforts of astronomy. The sky looks silent, but it is full of pattern. The universe looks cold, but it is full of relation. And the galaxy looks like a scattered band of stars, when in truth it is a system so deep and organized that it can hold its members for ages beyond imagination. So why do stars not simply drift away? Because drifting is not their natural state. Because they are moving within a gravitational design too deep to leave casually. Because their sideways motion keeps them in orbit instead of collapse. Because their speed, though enormous, is still usually not enough for freedom. Because a galaxy is not a random collection of lights. It is a bound, dynamic structure built from balance. And maybe, most quietly of all, because the universe seems to love these long forms of order. It loves the patient arrangement of matter into stars, the patient arrangement of stars into galaxies, and the patient motion that allows those galaxies to persist for billions of years. The stars do not simply wander off because the cosmos has built something stronger than wandering. It has built a home made of motion. And once you understand that, the next question begins to sharpen. If stars are already moving so fast, and if that motion is still not enough to set them free, then what exactly would be enough? What kind of speed does escape really require? How do astronomers draw the line between a star that remains bound and one that is truly on its way out forever? That is where the idea of escape velocity enters the story in its full galactic form. And that is where the challenge starts to become even more extreme. Part 5: The Problem of Escape Velocity. There is a strange comfort in looking at the night sky and imagining that space is open. No fences. No roads. No walls. Just darkness in every direction, waiting for anything with enough courage to cross it. From that point of view, escape can seem simple. You just keep going. You build a spacecraft, point it away from home, and continue forward for long enough. Eventually, surely, you must leave. Surely distance itself must solve the problem. Surely there must come a point where the galaxy loosens its grip and lets you drift into the deeper dark between galaxies. But the universe is rarely that intuitive. Because escaping a galaxy is not mainly a problem of distance. It is a problem of energy. It is a problem of whether your motion is enough to overcome the gravity of everything holding you. Not just for a little while, and not just at one moment, but permanently. To truly escape, you do not merely travel far. You cross a threshold. You move from being bound to being unbound. And the name we give to that threshold is escape velocity. If you like these quiet cosmic journeys, you can leave a gentle like, subscribe if you want more slow explorations like this, and share where you're listening from tonight. There is something calming about imagining all these thoughts traveling softly through different rooms and different nights, while the same sky stretches over all of them. Now, the phrase escape velocity can sound technical at first, but the core idea is beautifully simple. Imagine throwing a ball upward from the earth. If you toss it lightly, it rises and falls back. If you throw it harder, it goes higher, but still returns. Throw it harder again, and it climbs even farther. Gravity keeps tugging on it the whole time. It slows the ball, steals its upward speed, and eventually pulls it back down. But if the ball could leave your hand fast enough, something remarkable would happen. It would never come back. It would keep climbing away, slowing as it goes, but never slowing all the way to a stop before freedom is achieved. It would have enough energy to escape the Earth entirely. That minimum speed is Earth's escape velocity. It is not the speed needed to keep going forever at full pace. That is an easy thing to misunderstand. Escape velocity is simply the speed required at the beginning so that gravity cannot fully reclaim you. Once you have that much energy, you can slow down later and still remain free. You have crossed the line. That is what makes the idea so powerful. Escape velocity is not about comfort. It is about sufficiency. Not about traveling quickly for the sake of speed, but about beginning with enough energy to no longer belong to the system you are leaving. And this idea scales upward. There is an escape velocity from Earth. There is one from the Sun. And, more quietly and more overwhelmingly, there is one from the galaxy. That is where the story becomes truly humbling. Because people often hear about rockets escaping Earth and assume the same logic can simply be stretched upward without becoming too dramatic. We escaped our planet, after all. We sent probes to the outer solar system. Voyager 1 and Voyager 2 are moving through the dark far beyond the major planets. Human technology has already shown that gravity can be beaten. And that is true, in a limited sense. We can escape Earth. We can, with enough planning and fuel, escape the Sun's immediate hold as well. But escaping the galaxy is another matter entirely. Because each gravitational well sits inside a larger one. Earth orbits the Sun. The solar system travels inside the Milky Way. So if you launch a spacecraft from Earth, you are not starting from stillness. You are beginning inside layers of motion and layers of gravity. First you must climb out of Earth's grip. Then you must reckon with the Sun. And after that, you are still deep inside the galaxy's much larger hold. It is like climbing out of a small valley only to discover that valley was nested inside a mountain basin, and that basin was itself inside a vast continental depression. Freedom exists, but each layer asks more of you. That nested structure is one reason galactic escape is so difficult to picture. Our minds prefer simple boundaries. We like the thought of leaving one thing and then being done with it. But the universe is not arranged in clean, human-friendly steps. It is layered. The forces overlap. And a spacecraft that feels gloriously free of Earth can still be a complete prisoner of the Milky Way. That is not a metaphor. That is physics. Voyager 1, for example, is often described as having left the solar system in a practical sense, because it has moved beyond the heliosphere, the great bubble of solar influence carried outward by the solar wind. It is unimaginably far from Earth by human standards. It took light many hours to cross the distance between us and it. For a machine built by human hands, it is almost absurdly remote. And yet, on the scale of the galaxy, Voyager 1 has barely gone anywhere. It is still deeply, thoroughly inside the Milky Way. It is still orbiting the galactic center along with the Sun. It is still a passenger inside the same larger structure. Its freedom from Earth does not mean freedom from the galaxy. That contrast is worth lingering over, because it reveals something essential about escape velocity. Escape is always relative to the system doing the holding. A speed that is enough to leave one system may be laughably small for another. To escape Earth, you need one threshold. To escape the Sun from Earth's orbit, you need a much greater one. To escape the galaxy from our location within it, the required speed becomes more extreme still. And this is where intuition begins to soften under the weight of scale. Because the Milky Way is not just big, it is deep. Its gravity is spread across a region so vast that even enormous speed can still leave you bound. A useful way to think about escape velocity is to imagine rolling a ball out of a bowl. If the bowl is shallow, a modest push may be enough. The ball climbs the side and passes over the rim. If the bowl is deeper, you need more energy. Push too gently and the ball rises for a while, slows, and rolls back inward. Push hard enough and it crosses the edge and never returns. Now imagine a bowl so large that, while you are still inside it, the curvature feels almost flat. You may travel a long way and still not realize how deep the structure really is. That is much closer to what a galaxy is like. The gravitational well is not a sharp pit you can easily see around you. It is broad and immense. You can move within it for millions of years, covering astonishing distances, while still remaining very much inside. That is why distance can be so deceptive. A spacecraft can travel far and still not be escaping. A star can orbit at tremendous speed and still not be escaping. Even an object that feels as though it is rushing through free space may still be climbing only partway up a galactic slope. This is the quiet cruelty of escape velocity. It does not care how impressive the journey feels from inside it. It only cares whether the energy is enough. That also explains why escape velocity is tied so closely to mass. The more massive the system, the deeper the gravitational well. The deeper the well, the more speed you need to get out. Earth has one escape velocity. The Sun, because it is far more massive, has a much larger one. A galaxy, containing hundreds of billions of stars and vast amounts of other matter, becomes something else entirely. And yet there is a subtle point here that makes the subject even more fascinating. Escape velocity depends on where you start. If you are deep inside a gravitational system, you need more energy than if you begin farther out. Escaping Earth from the surface is harder than escaping Earth from high orbit. Escaping the Sun from near the Sun is harder than escaping it from the outer solar system. And escaping the galaxy from our position inside the Milky Way depends on the gravitational environment around our own neighborhood. This is one reason the problem is not usually described with one magical number that solves everything in every location. There are estimates for how fast an object would need to move, relative to the galaxy, to become unbound from our region. Those values are extremely high, far beyond the speed of ordinary human spacecraft. But the deeper point matters more than the exact figure. The point is this: the galaxy requires an absurd amount of speed. Not because the galaxy is malicious, but because it is massive. Because gravity, added up across so much matter, makes freedom expensive. That expense becomes easier to feel when we compare escape to orbit. An orbiting object is like a traveler circling a city on a ring road. They are moving quickly, even beautifully, but their path keeps them in relation to the center. Escape is different. Escape means having enough motion to stop circling altogether. Enough energy to keep moving outward without the system ever reclaiming you. In a way, orbit is a compromise. Escape is a refusal of the compromise. And the galaxy does not allow that easily. This is why stars, even very fast ones, usually remain members of the Milky Way. Their speeds are tremendous, but their motion is still arranged within the rules of being bound. They are not exceeding the local cost of freedom. They are participating in the long economy of galactic motion, where gravity continuously shapes their paths into belonging. Only in rare cases does a star gain enough speed to leave for good. When that happens, the star becomes something extraordinary, a true exile from the galaxy. But those cases are rare precisely because the threshold is so severe. For most stars, and certainly for most spacecraft we could imagine building, the galaxy's escape velocity remains a distant and almost brutal requirement. There is also another reason this subject feels so counterintuitive. In daily life, we associate freedom with persistence. If you keep walking long enough, you arrive. If you keep driving, you get farther away. Effort accumulates into distance, and distance becomes escape from where you started. But in a gravitational system, persistence alone is not enough. You can keep going forever and still remain bound, if your energy was never sufficient to cross the threshold in the first place. That is one of the strangest truths in astronomy. Endurance is not the same as escape. A star can endure for billions of years and never leave the galaxy. A spacecraft can travel for ages and still remain a galactic captive. Freedom is not guaranteed by time. It is decided by energy. And that changes the emotional shape of the whole problem. Leaving a galaxy is not like a road trip. It is more like trying to climb out of a basin that extends beyond the horizon, where every upward gain is taxed by gravity. You may rise for a while. You may travel astonishing distances. But unless your initial motion was enough, the system still owns your future. That is why escape velocity feels almost unforgiving. It draws a hard line through a universe that otherwise seems full of gradients. You are either bound or unbound. You either have enough or you do not. And that line can sit at values so high that even our boldest machines remain far below it. It is worth remembering how extraordinary that is. Humanity often feels technologically powerful because we have learned to cross oceans, fly through the air, and leave our planet. And on a human scale, that power is real. It is one of the great stories of our species. But the galaxy places that achievement in a wider frame. It reminds us that escaping Earth, magnificent as it is, was only the first rung on a cosmic ladder that keeps rising beyond comfortable imagination. The Milky Way is not just a backdrop to our ambitions. It is a limit we barely know how to describe. And yet the idea of escape velocity is not only humbling, it is clarifying. It tells us why galaxies can endure. It tells us why stars remain bound. It tells us why motion alone is not enough. It gives us a language for the difference between traveling within a system and truly leaving it. Without that idea, everything can seem vague. With it, the problem sharpens. We stop asking how long it takes to get out, and we start asking what kind of speed the universe demands. That is the real question. Not how patient you are, not how far the edge appears, but whether you can ever begin with enough energy to stop belonging to the galaxy at all. And when you frame it that way, the Milky Way starts to feel less like a collection of stars and more like a vast physical claim, a structure so massive that freedom from it requires something close to violence. Not violence in the emotional sense, but in the energetic one. A burst of motion so extreme that the galaxy can no longer bend your path back into orbit. That is what escape velocity means. The minimum speed needed to say goodbye in a language gravity understands. It is a hard language, a quiet one, and it is written not in words, but in motion. From where we are, deep inside the Milky Way, that required motion is far beyond what human life usually pictures when it dreams of interstellar travel. It is not just difficult, it borders on the absurd. And the deeper we look into our own galaxy, the more obvious that becomes. Because the Milky Way is not a simple swirl of visible stars. It is a gigantic system with a crowded center, extended arms, old halo populations, hidden mass, and a gravitational reach that stretches far beyond what the eye first notices. The speed required to leave all of that behind is not merely a technical challenge. It is a statement about scale. It is the universe reminding us that being small is not a flaw. It is simply a fact. And perhaps there is something soothing in that too. To understand escape velocity is to understand that the cosmos has depth, that structures are real, that we are not floating randomly in empty blackness, but living inside nested worlds of influence and motion. The same rule that makes freedom difficult also makes order possible. It is why stars stay in galaxies. It is why galaxies keep their shape. It is why the sky above Earth is not just chaos. The threshold is severe because the structure is real. And now that we have that threshold in mind, the next step becomes unavoidable. We have talked about galaxies in general. We have talked about the concept of escape. But what about our own home? What about the Milky Way specifically? How large is the system we are trapped inside? How much mass does it contain? How deep is the well from our own location within it? Because once we bring the Milky Way itself into focus, escape stops feeling abstract. It starts to feel nearly impossible. Part 6: Why the Milky Way is harder to leave than it looks. From a distance, the Milky Way can sound almost manageable. It is called a galaxy, yes, and everyone knows a galaxy is large, but the word itself can become so familiar that the size begins to blur. We hear it often enough that it starts to feel like just another category. Planet, star, solar system, galaxy. The mind places them in order, nods quietly, and moves on. But the truth is that the jump from a solar system to a galaxy is not just a bigger version of the same thing. It is a different kind of scale. And that difference matters. Because once you begin to understand the size and mass of the Milky Way in even a gentle, human way, the idea of leaving it starts to feel less like a difficult journey and more like an almost unreasonable demand. Not because space is dramatic, and not because the galaxy is hostile, but because the structure we live inside is so immense that our usual instincts about distance and motion stop being useful almost immediately. That is what makes the Milky Way so deceptive. It does not look impossible. It looks soft. If you have ever been somewhere truly dark, away from bright cities and electric haze, you may have seen it clearly. A pale river of light, a faint brightening stretched across the sky. Something dusty and delicate, almost like breath on black glass. It does not look heavy. It does not look like a prison. It certainly does not look like one of the deepest gravitational systems a human being could ever hope to imagine from the inside. And yet that is exactly what it is. The Milky Way is harder to leave than it looks because almost everything about it is more serious than it first appears. It is larger than intuition expects. It contains more mass than the eye can see. Its gravitational influence extends farther than its bright band of stars suggests. And we, on our quiet little world, are not standing near some convenient edge. We are living well within the system, already moving with it, already claimed by its gravity long before we begin to dream of leaving. If you enjoy these slow cosmic journeys before sleep, you can leave a quiet like, subscribe if you want more calm explorations like this, and share where you're listening from tonight. There is always something strangely comforting about the thought that while one person listens under rain, another listens under heat, another under city lights, and all of them are still under the same galaxy. To begin feeling the problem properly, it helps to start with a simpler mistake. Most people, when they first imagine the Milky Way, picture something like a flat spiral disk and assume that if a spacecraft could just keep traveling outward long enough, eventually it would pass through the bright part and be free. In that picture, the galaxy is almost like a photograph with a visible edge. Once you go beyond the light, you are done. That is a very human way of thinking. We trust what we can see. We assume that the bright part is the important part. We think of structure in terms of borders. But the Milky Way is not a painting with a clean frame. It is not even a neat wheel with a clearly marked rim. It is a layered gravitational system. There is the bright disk where many of the visible stars live. There is the central bulge, crowded and powerful. There are older stars and star clusters moving through the halo. There is gas, dust, and extended matter far beyond what the night sky itself makes obvious. So even before we reach the deeper mystery of hidden mass, the galaxy is already larger and more spread out than its soft luminous band suggests. This is the first reason it is harder to leave than it looks. What looks like the galaxy is not all of the galaxy. And what looks like the edge is not really the edge. Even the word edge becomes a little slippery here. We use it because the human mind wants a border, but galaxies are not built that way. Their visible density fades gradually. Their gravitational influence fades gradually. There is no bright painted line in space where the Milky Way ends and freedom begins. There are only regions where the pull becomes weaker and weaker with distance. To leave such a system, you do not cross one clean boundary. You keep climbing out of a deep and sprawling gravitational claim. That claim is easy to underestimate because the sky gives us the wrong emotional signal. It looks light. But a galaxy is not light in the physical sense that matters for escape. The Milky Way contains a staggering number of stars. Not dozens. Not thousands. Not even millions. On the scale of ordinary human thought, it contains so many that the number stops behaving like a number and turns into atmosphere. And every one of those stars has mass. Every cloud of gas has mass. Every dark remnant, every cluster, every thickened region of the disk, every contribution adds to the whole. Gravity does not care whether the mass is beautiful, or bright, or visible in some romantic way. It simply adds. That is why the galaxy's softness is misleading. A pile of feathers and a pile of stones may look different, but gravity only asks what is there. A galaxy can appear elegant and still be crushingly serious in terms of mass. And the Milky Way is serious. It is one thing to say that in abstract terms. It is another to let it settle into the imagination. Because on Earth, large things remain human-sized in comparison to us. A mountain is enormous, but we can still see it. An ocean is vast, but we can cross it with enough time and engineering. Even a whole planet can be pictured, held in one mental frame. The Milky Way resists that kind of framing. Its scale is too broad to live comfortably inside the ordinary imagination. The distance from one side of the visible disk to the other is so large that light itself, moving faster than anything in the everyday world, needs immense stretches of time to cross it. That fact alone should make the problem feel heavier. When even light takes a very long time to move across a structure, then any human-made object is entering a challenge so severe that language begins to soften around it. This is why leaving the Milky Way is not just difficult in the way climbing a mountain is difficult. It is difficult in the way outliving a continent would be difficult. The comparison breaks, of course, but that is the point. We reach for earthly metaphors because the true scale is too wide to carry directly. And yet the real cruelty of the Milky Way is not only its size. It is our location inside it. We are not perched near the outskirts with 1 foot almost free. We are not standing in some outer region where the galaxy's influence is already fading into almost nothing. Our solar system lives comfortably inside the galactic disk, not at the center, which would bring its own complications, but very much within the body of the galaxy. We are members of the system, not bystanders near its door. That means any dream of galactic escape begins from within the hold, not near its release. This is an important emotional correction. It is easy to imagine ourselves as looking outward from a place of possible departure. But physically, we are more like people deep inside a large city, speaking casually about how simple it might be to leave the country. Before the road even begins, we are surrounded by structure. We are already inside the traffic, already inside the laws of motion, already sharing the movement of the whole. The sun itself is orbiting the galactic center. The Earth travels with it. Every spacecraft we have ever launched begins its journey from a planet orbiting a star that is already moving inside a galaxy. So the problem is never just about accelerating a machine from rest. There is no rest. We begin in inherited motion. We begin inside a layered system. We begin in the middle of a story already being written by gravity. And that makes every step more expensive. To feel this properly, consider how easily our achievements can fool us. Human beings have done astonishing things. We learned to leave the ground. We reached orbit. We sent people to the moon. We launched robotic explorers outward through the solar system. We placed probes near giant planets. We crossed the great local distances that once felt almost mythical. On the scale of human history, those are breathtaking accomplishments. On the scale of the Milky Way, they are still almost intimate. The distances we celebrate, and rightly celebrate, are tiny compared with the breadth of the galaxy. The speeds we call extraordinary remain far below what galactic freedom demands. Even the most distant probes ever launched by humanity are still so deeply inside the Milky Way that speaking of galactic escape in the same breath can feel almost unfair. But unfairness is one of the universe's quieter habits. It does not grade effort by emotion. It does not reward ambition simply because ambition is noble. Gravity asks only whether the numbers are enough. And in the case of the Milky Way, the numbers are merciless. This is where the size of the galaxy and the depth of its gravity merge into one problem. A large system is not automatically a hard system to leave, but when that large system also contains enormous mass, spread through a wide and structured region, escape becomes something very different from ordinary travel. You are not just crossing empty space. You are continuously trying to overcome the pull of the whole while moving through it. That means a spacecraft leaving the solar system is not yet doing the most serious part of the work. Even after escaping the sun, it remains inside the galaxy's larger basin. Even after passing beyond familiar planets and beyond the local bubble of solar wind, it remains a creature of the Milky Way. The scenery may feel lonelier. The distances may feel more severe. But gravitationally, the machine is still inside the long reach of home. There is something deeply humbling about that. We like to imagine escape as dramatic, a breaking away, a clean moment of release. But galactic reality is quieter and less theatrical. You can move unimaginably far from Earth and still not be close to leaving the galaxy. You can enter regions so dark and remote that the solar system feels like a myth behind you, and still the Milky Way has not let go. That is how large the system is. That is how patient its gravity is. And then, just when the visible scale already feels overwhelming, there is another complication. The Milky Way seems to contain more gravitational influence than visible matter alone should provide. We have been circling this idea gently for a while, and here it begins to matter more. If the galaxy were only the stars we see and the ordinary matter we can easily account for, escaping it would already be extraordinary. But the evidence suggests the Milky Way is surrounded by a much larger halo of unseen mass. Not bright, not obvious to the eye, not something the night sky announces. And yet its gravitational role appears to be profound. This means the galaxy is not only what it looks like. It is heavier than it looks, wider than it looks, more binding than it looks. That hidden depth changes the emotional shape of the problem. It is like discovering that the quiet hill you planned to climb is actually the visible top of a mountain whose true body disappears into cloud and stone beneath your feet. The challenge was not what you thought it was. The visible part was only the introduction. So when someone says they want to leave the Milky Way, what they are really saying is that they want to overcome not just the bright disk of stars, not just the ordinary mass of a visible galaxy, but the full gravitational architecture of a structure whose deeper weight is partly hidden from sight. That is one reason the idea carries such a strange combination of beauty and impossibility. It sounds poetic, but physically, it is brutal. And still, there is more. The Milky Way is not alone in a perfectly empty setting. It belongs to a larger environment. Nearby dwarf galaxies, the wider local group, the presence of Andromeda, the broader cosmic web, all of these remind us that no structure in the universe exists in splendid isolation. Now, for the question of simply escaping our own galaxy, the Milky Way itself is the main challenge. But the larger cosmic context adds a subtle feeling of enclosure. Freedom from one system does not mean freedom from all systems. The universe is built in layers of belonging. Planets inside star systems inside galaxies, galaxies inside groups, groups inside larger patterns. At every scale, the dream of open emptiness meets structure again. That is not a reason to feel trapped in any ordinary emotional sense. In fact, there can be something soothing in it. But it does make the phrase "just leave" feel almost childlike in its innocence. There is no just about it. Not when the structure in question is a galaxy. The Milky Way is harder to leave than it looks because its appearance encourages the wrong kind of confidence. We see a glowing band and think in terms of scenery. We should be thinking in terms of mass. We imagine a distant rim. We should be thinking in terms of a fading gravitational field with no sharp farewell. We picture ourselves as observers. We should remember that we are residents. And perhaps most importantly, we mistake the size we can emotionally feel for the size that physics actually measures. That gap between feeling and reality is one of astronomy's oldest lessons. The moon looks close enough to touch, yet it is not. The stars look small, yet many are unimaginably large. The Milky Way looks like a quiet mist, yet it is one of the dominant structures of our existence. That soft-looking band has held our sun for all of its life. It has held the matter that became Earth. It has held the long conditions under which oceans formed, continents shifted, life emerged, and minds began asking questions about freedom. The same structure that makes escape nearly absurd is also the structure that allowed our home to exist in the first place. That is worth pausing over. Because when people hear that the galaxy is hard to leave, the thought can sound oppressive, almost claustrophobic. But there is another way to feel it. The Milky Way's gravity is not only a barrier. It is also a long form of protection. It is the reason our region of the universe has had continuity. It is the reason stars remain in shared motion rather than scattering into pure chaos. It is the reason the night sky is not random noise. The galaxy's hold is what makes the galaxy a home. And perhaps that is why the subject feels so haunting. To speak about escape is also to speak about belonging. To wonder how one might leave is to realize how deeply one has been held all along. The difficulty of departure is the measure of the structure's reality. A house you can walk out of casually was never much of a house. A galaxy that could not hold its stars would never have become a galaxy at all. So yes, the Milky Way is harder to leave than it looks. Harder because of its size. Harder because of our position within it. Harder because visible light understates the system. Harder because gravity does not end where brightness fades. Harder because the cost of freedom is set by the full mass of the whole, not by the softness of what our eyes happen to notice. And the deeper you let that sink in, the more the next question begins to gather. If the Milky Way is already this difficult to leave based on its visible size and structure, then what role does that hidden mass really play? How much of the galaxy's grip comes from what we cannot see? How much harder is escape because of the weight living in darkness around us? That is where the story grows stranger still. Because much of the galaxy's power may come from something invisible. Part 7, The Hidden Weight of Dark Matter. There is something unsettling, and strangely beautiful, about realizing that a galaxy may be far heavier than it looks. Not a little heavier. Not slightly more complicated than the eye first suggests. But profoundly heavier, in a way that changes the meaning of everything inside it. When we look at the Milky Way, or at any spiral galaxy, we naturally trust the light. We see stars. We see glowing bands. We see bright central regions and scattered clouds of gas. And because light is what reaches us, light becomes our first instinct for judging what is there. We assume the visible parts are the main parts. We assume the shining matter tells the story. But one of the quietest shocks in modern astronomy is that the light does not tell the whole story. Not even close. There appears to be far more mass in and around galaxies than we can directly see. A hidden weight. A dark framework. Something that does not shine like stars, does not glow like gas, does not reveal itself in the ordinary way, and yet still exerts gravity with enormous influence. And if that is true, then escaping a galaxy is not just difficult because of the stars we see. It is difficult because much of the galaxy's grip may come from something invisible. If you enjoy these slow journeys through space before sleep, you can leave a quiet like, subscribe if you want more calm explorations like this, and share where you're listening from tonight. It is always comforting to imagine the same galaxy hanging above so many different sleeping places at once. To begin understanding this hidden weight, it helps to return to a very simple expectation. If most of a galaxy's visible matter is concentrated more toward the center, then you might naturally expect stars farther out to move more slowly in their orbits. That would feel intuitive. We already see something like that in the solar system. The planets closer to the sun move more quickly. The ones farther out move more slowly. The farther you get from the main concentration of mass, the weaker the pull becomes, and the less speed is needed to remain in orbit. So early on, astronomers expected galaxies to behave in a somewhat similar way. The bright central regions should matter most. The outer stars should slow down. The visible structure should more or less explain the motion. But when astronomers studied real galaxies carefully, especially the speeds of stars and gas at different distances from the center, something did not fit that expectation. The outer regions were often moving faster than they should have been, if the galaxy contained only the mass we could see. Instead of the speeds dropping off in the neat way intuition suggested, they stayed surprisingly high. That was the problem. And it was a serious one. Because motion is evidence. A star's path tells you something about the gravity acting on it. If something far from the center is still moving very quickly without flying away, then the galaxy must be exerting more pull there than visible matter alone seems able to provide. In other words, the galaxy appears to have extra mass. Mass that does not announce itself through light. Mass that still makes itself known through gravity. That is where the modern idea of dark matter enters the story. The name itself can sound dramatic, almost like something invented for science fiction. Dark matter. It carries a certain mystery with it. But the idea behind the name is more careful than mystical. It does not mean evil matter, or magical matter, or a substance made of literal darkness. It simply refers to matter, or something behaving like matter gravitationally, that does not emit, absorb, or reflect light in the familiar way we would expect from ordinary visible material. We call it dark because it does not shine for us. But its gravity still counts. And that invisible gravity seems to matter enormously. This is one of those rare ideas in science that feels both abstract and deeply physical at the same time. You cannot point to dark matter in the sky the way you can point to a bright star. You cannot hold it in your imagination as easily as a planet or a moon. Yet its consequences may shape the entire motion of galaxies. It may be one of the main reasons galaxies hold together as strongly as they do. That is why it belongs in this story. Because once dark matter enters the picture, escaping a galaxy stops being merely a problem of visible stars and glowing gas. It becomes a problem of hidden architecture. A problem of climbing out of a structure that is only partly illuminated. A good way to feel this is to imagine walking through an old house at night with only a small lamp. You see the furniture near you. You see the walls in one room. You can make out the visible arrangement of things. But suppose the house is much larger than the part your lamp reveals. Suppose there are heavy beams, locked rooms, staircases, foundations, and entire wings disappearing into darkness. If you judged the structure only by what the lamp touched, you would misunderstand the true size and weight of the place you were standing in. That is a little like what dark matter does to our picture of a galaxy. The stars are the lit furniture. The full structure is larger. And gravity feels the whole house, not just the parts we can see. One of the most important things to keep in mind here is that dark matter was not imagined simply because astronomers liked mystery. It emerged because the visible explanation did not seem sufficient. The galaxies were behaving as though more mass was present. The motion kept pointing towards something missing from the bright picture. That is how science often moves forward at its best. Not through fantasy, but through stubborn mismatch. Reality refuses to fit the simple expectation, so we are forced to widen the frame. And galaxies did refuse. Again and again, their outer regions seemed too fast, too well held, too strongly bound for visible matter alone to explain comfortably. There are other clues too, beyond the motion of stars inside galaxies. Entire clusters of galaxies also seem to contain far more gravitational influence than visible matter would suggest. Light from distant objects can be bent by gravity in ways that point to extra unseen mass. Large-scale structures in the universe appear to have grown in ways that also fit the presence of some non-luminous matter. So the case for dark matter does not rest on one single observation. It comes from a wider pattern. Still, for our purposes, the galactic picture is enough. The Milky Way may be sitting inside a huge halo of dark matter. Not a bright halo. Not something beautiful in the visual sense. But a gravitational halo, extending far beyond the familiar luminous disk. And if that is true, then the problem of escape becomes much more serious than it first appears. Because now, even after you leave behind the bright arms, even after the visible stars begin to thin, even after the glowing shape of the galaxy looks distant behind you, the hidden mass may still be exerting its claim. This is why dark matter matters emotionally as much as scientifically in this story. It tells us that the galaxy's grip is deeper than the scenery suggests. The stars are not the whole cage. The light is not the whole hold. What seems visible and beautiful from far away may sit inside a much larger invisible basin of gravity. That changes the texture of escape. Without dark matter, leaving the Milky Way would already be extreme. With dark matter in the picture, the galaxy becomes even less like a pinwheel of stars and more like a deep gravitational continent whose true edges live partly in shadow. There is something haunting about that. The universe is often described as cold, dark, and empty. But dark matter suggests a subtler kind of darkness. Not empty darkness, but structured darkness. Not the absence of influence, but influence without light. Something can be unseen and still shape everything around it. In human life, we are used to equating visibility with importance. What is obvious feels real. What can be measured directly feels trustworthy. What can be touched feels central. But astronomy keeps teaching us the same quiet lesson. The universe does not owe us easy perception. Some of its most important structures do not present themselves in forms our instincts are built to notice. Dark matter may be one of those structures. And perhaps that is why it captures the imagination so strongly. It is not just a scientific puzzle. It is a philosophical one too. It reminds us that reality is not limited to what glows. Still, it is important to stay grounded. Dark matter is not a blank check for wild speculation. It does not mean anything mysterious can be true. It is not simply a name for ignorance. It is a model built to account for gravitational effects that visible matter does not seem to explain well enough. Scientists continue to test it, question it, refine it, and compare it with alternatives. There are still open questions. There are still debates about the deeper nature of the phenomenon. That uncertainty is real. But uncertainty does not mean the underlying problem disappears. The galaxies still behave as though something extra is there. The Milky Way still appears to be held together by more than its stars alone. And if we are asking why escaping a galaxy is so difficult, then that hidden contribution cannot be ignored. One calming way to picture it is as an invisible landscape surrounding the visible galaxy. Not a wall, not a shell, not a sharply defined barrier. More like a broad gravitational mist of mass, though not mist in the ordinary material sense. A vast unseen component that deepens the overall basin in which the visible galaxy lives. The stars are embedded in it. Gas moves within it. Whole galactic structures seem shaped by it. And because it extends far beyond the bright disk, it makes the galaxy bigger in the sense that matters most for escape. This is also why saying leave the galaxy can be misleading in a deeper way than before. If you are thinking only about the bright stars, you are thinking visually. But gravity is not a visual experience. Gravity does not stop where the eye stops. So the real question is not when the galaxy stops looking like a galaxy. The real question is when the full gravitational system, visible and invisible together, stops being able to call you back. That question is much harder. And much darker. Another way to feel the role of dark matter is to think about what it means for stars in the outer galaxy. Without enough mass in the system, those outer stars should be much more weakly held. Some would likely move differently. The clean visible picture would not be stable enough to explain the motions we observe. But if a large invisible halo surrounds the galaxy, then those stars are not merely orbiting a bright spiral. They are moving inside a much deeper gravitational environment than the luminous structure alone would suggest. It is as though the visible galaxy is the lantern, but the true structure is the valley around it. That hidden valley matters. And it matters not just for stars, but for anything trying to leave. A spacecraft, no matter how advanced, would not be negotiating only with visible matter. It would be negotiating with the whole gravitational profile of the Milky Way. The glowing disk, the central concentration, the gas, the stellar populations, and beyond them, the hidden mass that may dominate the galaxy's overall weight. In that sense, dark matter changes the character of the challenge from difficult to deeply unfair, because it means part of what is holding you does not even reveal itself gracefully. The galaxy asks for more energy than its appearance seems to justify. And of course, that makes intuitive sense only after you let go of the idea that appearance should be enough. The night sky is full of examples where appearance misleads us. A bright nearby planet can look more important than a vast distant star. A nebula can look larger than it is, or smaller. A tiny point of light may conceal a whole galaxy. The Milky Way itself looks like a band, when in fact it is the inside view of an enormous spiral system. So perhaps dark matter is simply one more reminder that the universe is not arranged for visual comfort. We are not promised a transparent cosmos. We are only promised that patterns, if observed carefully enough, will begin to reveal what is there. And in this case, the pattern says hidden mass. There is another emotional layer to this too. Dark matter means that much of the universe's structure may be built on something we still do not fully understand. Not just galaxies, but the broader cosmic web, the large-scale growth of order, the deep scaffolding of matter across the universe. That can sound unsettling at first, but there is a quiet comfort in it as well. It means the cosmos is still larger than our current explanations. There is still room for wonder that is real, disciplined, and patient. Wonder does not end when science names a thing. Sometimes it deepens. And dark matter is one of those names that deepens wonder. It does not solve the mystery in a final emotional sense. It simply tells us that the mystery has structure. Now, it is worth saying one more practical thing. Dark matter is not just ordinary dark stuff hiding in the corners. It is not likely to be explained simply by faint stars we forgot to count, or clouds of dust, or wandering planets alone. Those ideas were considered, and the evidence seems to point to something more substantial and more unusual. Whatever dark matter is, if the dominant picture is correct, it represents a major component of galactic mass that behaves differently from ordinary visible matter in terms of how it interacts with light. That is an extraordinary statement. Much of what gives the Milky Way its gravitational depth may be something fundamentally unlike the stars we admire. And yet from the standpoint of escape, the distinction almost stops mattering. Whether a kilogram shines or not, gravity includes it. Whether the mass comes from blazing stars or invisible particles, the basin gets deeper all the same. That is the cold fairness of gravity. It counts everything. So if we gather the lesson gently, it becomes this. The Milky Way is difficult to leave not only because it is large and full of stars, but because those visible stars may represent only part of the real mass involved. Around the luminous galaxy may lie a vast halo of dark matter, extending the reach and depth of the Milky Way's gravitational hold. The galaxy is not just what glows. It is also what weighs. And we live inside both. Inside the visible beauty. Inside the invisible pull. The more you let that settle in, the more the whole subject begins to change tone. Escaping the galaxy is no longer just a grand travel problem. It becomes a confrontation with hidden structure. It becomes a question of how any human-made object could ever overcome a system whose true weight is only partly visible. And perhaps that is why the Milky Way feels so different once dark matter enters the story. Before, it was a giant home. Now it is a giant home standing inside a larger invisible foundation. Before, it was hard to leave. Now it is hard in ways the eye never warned you about. There is a strange kind of humility in that. We often imagine that knowledge makes the universe smaller, more manageable, less mysterious. But sometimes knowledge does the opposite. Sometimes it reveals that what looked simple was only the lit surface of something much deeper. Dark matter does that to the galaxy. It turns a bright spiral into a partially hidden structure of enormous seriousness. And once you understand that, the next question becomes unavoidable. If the Milky Way is held together partly by all this visible and invisible mass, then what would actually happen if we tried to leave? Not in a vague poetic sense, but in physical terms. If a spacecraft set out with that goal, what would it be up against? How fast would it need to go? How long would the journey take? And how far is our technology from anything like that possibility? That is where the story becomes less mysterious, and somehow even more overwhelming. Because once we imagine an actual spacecraft trying to climb out, the scale stops being abstract. It becomes brutally personal. Part 8. What would happen if a spacecraft tried to leave? It is one thing to speak about escape in the language of stars and gravity. It is another thing to imagine a real machine trying to do it. The moment you bring a spacecraft into the picture, the whole subject changes shape. It becomes less like a grand idea and more like a physical struggle. You can begin to picture metal, fuel, engines, trajectories, long silence, and a machine moving farther and farther from everything familiar. You can imagine the Earth shrinking behind it, then the Sun becoming just another bright star, then the local neighborhood of space thinning into something colder and darker. And for a while, that image can feel almost heroic, almost convincing. It can feel like the beginning of freedom. But the deeper truth is much harder. Because if a spacecraft tried to leave the galaxy, it would run into one of the most brutal facts in all of astronomy. The universe does not care how far you have already traveled. It only cares whether you are still bound. And for an ordinary spacecraft, the answer would remain yes for an almost unimaginable length of time. If you enjoy these slow journeys through space before sleep, you can leave a quiet like, subscribe if you'd like more calm explorations like this, and share where you're listening from tonight. There is always something comforting about the thought that while one person listens under a bright city sky and another under a dark countryside sky, both are still traveling through the same galaxy together. To begin, it helps to start with a simple but important distinction. A spacecraft leaving Earth is not the same as a spacecraft leaving the solar system. And a spacecraft leaving the solar system is not the same as a spacecraft leaving the Milky Way. These are three very different achievements. Leaving Earth means overcoming the gravity of our planet. That alone is a major triumph of engineering. It requires extraordinary speed, precise launch timing, immense energy, and a machine capable of surviving one of the most violent transitions humans have ever learned to create. Leaving the solar system is a much larger challenge. It means not only escaping Earth, but escaping the deeper gravitational control of the Sun. You have to build enough speed that the spacecraft is no longer just circling within the family of planets. It must become unbound from the star that dominates our local space. But leaving the galaxy is larger again by a degree that almost stops feeling like the same category of problem. Because by the time a spacecraft has escaped Earth and then escaped the Sun, it still remains deep inside the Milky Way. It is like someone who has left their house, then left their city, only to realize they're still inside an entire continent whose borders are far beyond anything they had emotionally prepared for. That is where the ordinary imagination begins to strain. We are used to thinking in ladders of progress. First one threshold, then the next. Earth, then the solar system, then the stars, then the galaxy. The mind likes this kind of neat sequence. It feels orderly. It makes exploration seem like a longer version of travel. But the problem is that each rung is not just a little harder than the last. Each rung is vastly harder. A spacecraft can leave Earth with human technology. We have already done that. A spacecraft can be set on a path that eventually escapes the Sun's direct hold. We have done that too, at least in the sense of sending probes outward on escape trajectories from the solar system. But a spacecraft trying to leave the galaxy would face a completely different scale of difficulty. And perhaps the best way to feel that is to look at the most successful examples we already have. Voyager 1 and Voyager 2 are among the most extraordinary machines human beings have ever built. They were launched in the 20th century, and they are still traveling outward now, carrying human-made instruments and messages into the deeper dark. They have crossed vast distances by human standards. They have passed the giant planets. They have traveled beyond the heliosphere in practical terms. They are among the farthest artifacts our species has ever placed into space. And yet, in the story we are telling tonight, Voyager is still nowhere close to freedom from the galaxy. That is not criticism. It is perspective. Voyager is astonishing. The Milky Way is simply bigger. Much bigger. Deeper. Heavier. More patient. If you could somehow compare the path of Voyager to the scale of the galaxy in one glance, The effect would be almost shocking. The probe would no longer look like a triumphant escapee racing into the unknown. It would look more like a tiny object taking its first few steps inside an enormous landscape. Not because Voyager is unimpressive, but because the Milky Way is so overwhelmingly large that even our boldest journeys can become almost intimate by comparison. This is one of the reasons the question of a spacecraft escaping the galaxy feels so strange. It forces us to hold two truths at once. One is that human engineering is extraordinary. The other is that cosmic scale is indifferent to our sense of extraordinary. Now, suppose we imagine a spacecraft designed specifically for galactic escape. Not a probe built to study nearby planets. Not a machine designed for the outer solar system. But a true attempt to leave the Milky Way forever. What would happen? First, the spacecraft would have to begin by dealing with Earth, just as every spacecraft does. That means launch, acceleration, escape from the planet's gravitational grip, and survival through the violence of ascent. Then it would have to deal with the Sun. It is easy to forget that the solar system is not just a collection of planets floating peacefully together. It is a gravitational domain dominated by a star. To truly leave the solar system, the spacecraft would need enough energy to stop being a long-term participant in that system. That alone requires formidable speed. But even after achieving both of those things, the real problem would still only be beginning. Because the spacecraft would still be moving inside the galaxy. And more importantly, it would already be moving with the galaxy. This part matters more than it may seem. Earth orbits the Sun. The Sun orbits the center of the Milky Way. So any spacecraft launched from Earth begins with inherited motion. It is not sitting in a neutral void. It is born into a moving frame. The Earth is already carrying it. The Sun is already carrying it. The galaxy is already shaping the broader motion of all of it. That means the spacecraft's challenge is not merely to accelerate from zero. There is no zero. Instead, it must alter its motion enough, in the right way, to become unbound from the galaxy's gravitational hold. And that is much harder than just moving fast in some absolute sense. It depends on direction. It depends on location. It depends on the gravitational field around the solar system. And it depends on how much additional energy the spacecraft can gain beyond the vast inherited motion it already has. This is where the idea of a spacecraft becomes physically sobering. Because even if you imagine a machine traveling far faster than anything humans have launched so far, the galaxy may still not care very much. It may still see that machine as deeply bound. That is the real power of galactic scale. It makes speed look small. To understand what this means in practice, imagine a spacecraft with engines far beyond our current abilities. Suppose it could travel fast enough to make our present probes look almost still. Even then, leaving the galaxy would not mean a quick journey. It would still take an immense stretch of time. Not years in the ordinary sense. Not a single lifetime. Not even something easily held inside a civilization's normal planning horizon. The timescales grow so large that they begin to feel less like travel and more like inheritance. The spacecraft would outlast governments, languages, nations, perhaps entire human eras. It would continue through darkness long after the people who built it had vanished into history. Its mission would not be a mission in the way we usually understand missions. It would be a long active momentum carried across generations that would never meet its destination. And that is assuming it had enough speed in the first place. Without that, the journey would be even stranger. The spacecraft might travel for ages, crossing astonishing distances, moving through regions of space so remote that human intuition would describe them as almost free. But gravitationally, it could still remain bound to the Milky Way. It might still be climbing only part way out of the basin. That is one of the hardest truths in this entire topic. A spacecraft can feel lost and still not be gone. It can feel far beyond home and still belong to home. Distance creates emotion. Energy decides freedom. This is why a galactic escape mission is not just an engineering challenge, but a kind of philosophical shock. It reveals how inadequate our normal language of travel really is. On Earth, if something has gone far enough, we say it has left. But in astronomy, far enough is not measured emotionally. It is measured dynamically. A spacecraft may be unimaginably far from Earth and yet still remain part of the same galactic motion that began the moment it was launched. There is also the practical cruelty of propulsion. Rockets work by throwing mass backward to move forward. That is simple enough in principle, but terribly expensive in terms of fuel. To gain more speed, you generally need more propellant. But more propellant means more mass. More mass means you need even more energy to accelerate. This is one of the oldest difficulties in space travel. The faster you want to go, the more punishing the problem becomes. For interplanetary travel, this is already difficult. For interstellar travel, it becomes severe. For galactic escape, it becomes something close to absurd under ordinary propulsion methods. That is why people sometimes imagine more exotic concepts. Nuclear propulsion, fusion propulsion, light sails pushed by powerful lasers, antimatter ideas, generation ships, relativistic probes, thought experiments that try to stretch our current imagination toward something worthy of the scale involved. And these ideas are fascinating. They matter. They tell us that the human mind does not stop at present limitations. But even those more advanced concepts do not magically make the galaxy small. They only begin to make the challenge discussable. That is the difference. A more powerful propulsion system might one day let us think seriously about interstellar travel. It might shorten journeys that are otherwise hopeless. It might allow robotic explorers to reach other stars in timescales that are still long, but no longer ridiculous by cosmic standards. Yet galactic escape remains another level of seriousness. Because even if you could cross interstellar distances, the Milky Way contains a vast number of stars spread across an immense structure. You are not trying to reach one nearby point. You are trying to overcome a whole gravitational system and keep going until it no longer owns your path. That means the spacecraft's mission is not simply travel. It is severance. A true galactic escape vehicle would need to do more than survive the void. It would need to outrun belonging. There is something almost melancholy about that. Because once you imagine such a mission seriously, the romance of departure begins to change. It stops feeling like adventure in the ordinary sense and starts feeling like exile. A machine launched for galactic escape would be leaving not just Earth, not just the Sun, but the entire gravitational home of our star system. It would carry no realistic hope of return. It would not be visiting the deep. It would be abandoning one cosmic membership for another, smaller and lonelier state. Perhaps that is why the idea feels so emotionally charged. Even when we speak of spacecraft and trajectories, the deeper subject is still belonging. The galaxy is not just a place on a map. It is the system that has held our sun, our planet, and every human life that has ever existed. To leave it is not just to go far. It is to cease participating in the long motion of home. Of course, a machine does not feel loneliness. But we do. So when we imagine the spacecraft, we inevitably imagine it on our own terms. We picture it moving into deeper silence, farther from every familiar star field, beyond the bright band of the Milky Way, into regions where the galaxy becomes a distant object behind it. And the mind naturally asks what that would be like. Not just physically, but emotionally. What kind of journey continues after everything recognizable is gone? The answer, in a strict sense, is that the spacecraft would know nothing. It would simply continue according to the laws of physics. It would radiate heat, endure damage, accumulate wear, and perhaps eventually fail. It would move through sparse space, possibly for millions of years. If it were lucky, and built with impossible durability, it might go on far longer than any human institution. It would become a drifting consequence of one civilization's brief desire to touch the impossible. And that image is both sad and beautiful, because it reveals how large the galaxy really is. A machine can be built with extraordinary intelligence, launched with astonishing precision, and still spend most of its existence merely trying to get free. That is what would happen if a spacecraft tried to leave. It would discover that leaving is not a moment. It is a long, punishing negotiation with gravity. It would discover that Earth was only the first lock, that the Sun was only the second, that the galaxy itself is the great enclosing structure beneath both. And it would discover something else too, something perhaps even more humbling. It would discover that the visible stars are not the whole obstacle. The hidden mass of dark matter, the broad gravitational basin of the Milky Way, the immense scale of the system, all of that would remain part of the problem. The spacecraft would not simply fly through a beautiful spiral and emerge into open blackness. It would spend ages climbing through a galaxy whose true depth is only partly visible. And perhaps the most painful part is this: even if the spacecraft succeeded, the success would be hard to celebrate in any normal human sense. Why? Because success would come too late. Not late in a dramatic or emotional way, but late in the physical way that matters most. The timescales would likely dwarf individual lives. They might dwarf civilizations. The machine would continue beyond the meaning of the people who sent it. Its victory, if victory is the right word, would be mostly invisible to its creators. There is something very pure in that idea. A journey so large that it refuses human timing. A goal so distant that no applause could ever reach it. That does not make the mission meaningless. In some ways it makes it more profound. It turns the spacecraft into a kind of statement rather than a voyage. A declaration that intelligence inside one galaxy once wondered what lay beyond its own gravitational home, and dared to send something outward even though it would never live to see the answer. Still, it is important to remain honest. With current human technology, anything resembling a true galactic escape mission is not realistically within reach. The speeds required are too high. The energy demands are too severe. The travel times are too extreme. The engineering problems are too deep. We can dream about such things. We can model them. We can let them stretch our sense of what might one day be possible. But for now, the Milky Way remains a structure we understand far better than we can physically leave. And maybe that honesty is calming in its own way. We do not need to pretend that everything grand is near. Some frontiers are still allowed to be enormous. Some thresholds are still allowed to humble us. The galaxy is one of them. So what would happen if a spacecraft tried to leave? First, it would escape Earth, if it could. Then it would escape the Sun, if it had enough energy. Then it would continue outward into the long dark, carrying inherited galactic motion with it, trying not just to travel far, but to gain enough additional speed in the right way to become truly unbound from the Milky Way. It would cross regions of increasing loneliness. It would move through distances so large that human history would shrink into a footnote behind it. It would keep climbing through a gravitational landscape deeper than the visible galaxy suggests. And for a very long time, perhaps for longer than the builders could emotionally imagine, it would still belong to the very system it was trying to leave. That is the part that matters most. A spacecraft trying to escape the galaxy would learn that motion is not freedom. Not immediately. Not even after a triumph that feels absolute by human standards. The galaxy does not surrender its members easily. And once you see that clearly, the next question almost asks itself. If ordinary spacecraft are nowhere near enough, are there any things in the universe that really can escape a galaxy naturally? Do stars ever get thrown free? Do violent cosmic events ever create true exiles from galactic gravity? Does nature, in its own cold and dramatic way, sometimes achieve what our machines still cannot? That is where the story turns toward the rare exceptions. And the exceptions are as fascinating as they are unforgiving. Part 9. Can anything naturally escape a galaxy? By now, the Milky Way may be starting to feel almost inescapable. A structure so large that distance becomes misleading, so massive that speed begins to lose its meaning, so patient that even a spacecraft traveling far beyond the planets would still remain, in the deeper physical sense, one of its members. And if that is true, then a natural question follows. Does anything ever really get out? Not a probe, not some imagined future engine, but anything in nature itself. Anything born inside a galaxy, moving inside a galaxy, and then somehow leaving it behind forever. It is a beautiful question, because it carries a quiet hope inside it. If galaxies are this strong, then maybe escape is impossible. But if escape is possible, then somewhere in the universe there must be exiles. There must be stars that no longer belong to the galaxies that formed them. There must be objects that were once held and then, through some rare and violent turn of events, were released into the dark between galaxies. And the answer, softly, is yes. Nature does sometimes let things go, but it almost never does so gently. If you enjoy these calm journeys through space before sleep, you can leave a quiet like, subscribe if you want more slow explorations like this, and share where you're listening from tonight. It is always strangely comforting to imagine so many different people drifting through the same cosmic questions under the same unseen sky. The first thing to understand is that ordinary motion is usually not enough. A star can orbit a galaxy for billions of years. It can travel at extraordinary speed. It can move through spiral arms, through quiet neighborhoods, through denser regions and emptier ones, and still never come close to freedom. That is the normal story. That is the life most stars live. They are fast, but bound. They are active, but not free. So when something does escape naturally, it usually means something unusual has happened. Some powerful gravitational event. Some sudden transfer of energy. Some cosmic accident dramatic enough to turn a bound path into an unbound one. One of the most famous examples is something called a hypervelocity star. The name sounds almost too dramatic to be real, but it describes exactly what it means to describe. A star moving so fast that it can escape the galaxy it belongs to. Not merely racing through it. Not just traveling quickly within the system, but moving with enough speed, and in the right circumstances, to break free from the galaxy's gravitational hold altogether. That is extraordinary. A star is not a pebble. It is not dust. It is not some easily scattered particle. It is a sun, a true star. And yet even a star can, under rare circumstances, be flung outward so violently that the galaxy cannot keep it. How does that happen? Often, the answer seems to involve the galactic center. At the center of the Milky Way, and at the centers of many other galaxies, there is an extreme environment. Crowded, energetic, gravitationally intense. In the Milky Way's case, there is also a supermassive black hole there. An object of enormous mass whose presence shapes the behavior of matter and stars around it. Black holes often get treated like monsters in popular imagination, and sometimes that language hides more than it reveals. But in this case, the central black hole really can play a dramatic role. Imagine a binary star system, two stars orbiting one another, wandering too close to the galactic center. If that pair passes near the supermassive black hole in just the wrong way, the encounter can tear the partnership apart. One star may be captured into a new path, while the other gets hurled outward at astonishing speed, like a stone released from a sling. This is one of the leading ideas behind some hypervelocity stars. A star falls into the wrong conversation with a black hole, and the galaxy loses it. There is something almost mythic in that image. Two stars born together, living together, circling one another for ages, and then one violent encounter near the darkest place in the galaxy changes everything. One remains. One is thrown into exile. And yet this is not myth. It is physics acting under extreme conditions. Gravity, which usually binds, can also eject. That is one of the deepest and strangest truths in this whole story. The same force that keeps stars in orbit can, in special situations, fling them away forever. It all depends on the geometry of the encounter, the transfer of energy, the masses involved, and the exact path through the gravitational field. Most motion inside a galaxy leads to belonging. Rare motion leads to expulsion. The galaxy is usually a home, but in rare cases, it becomes a slingshot. Hypervelocity stars are compelling not only because they exist, but because they help prove a point we have been slowly building toward all night. Escape from a galaxy is possible in principle. It is not forbidden by nature. The threshold can be crossed. The bound can become unbound. But the manner of crossing matters. A hypervelocity star is not the result of patience alone. It does not simply wander for long enough and drift free. It is launched. There is a violence to it, an abruptness, a sudden gain of energy that ordinary galactic life does not provide. That tells us something important. Escape is not the natural outcome of time. It is the rare outcome of an event. And black hole encounters are not the only possible events. Sometimes stars can be accelerated by other gravitational interactions too. Dense star clusters can create complicated multi-body encounters. A star may pass close to other massive objects, exchange energy, and be kicked into a much more extreme path. These interactions are not as famous as the dramatic black hole scenario, but the principle is related. In crowded gravitational environments, motion can be reshuffled. One object may lose energy. Another may gain it. And once in a great while, the gain is enough to turn a member into an escapee. Still, not every fast star is truly free. This is another place where the universe asks us to be careful. There are runaway stars, for example, stars moving unusually fast compared with their neighbors. Some are launched by supernova explosions in binary systems. Imagine two stars living together in orbit. One of them explodes at the end of its life. The system is disrupted. The surviving star may be thrown outward at high speed. That speed can be impressive, and the story itself can feel dramatic, but not every runaway star has enough energy to leave the galaxy completely. Some are simply racing through it on altered paths, still bound to the Milky Way even if their local motion looks extreme. That distinction matters. Fast does not necessarily mean free. Again and again, the galaxy teaches the same lesson. A star can be moving in a way that looks astonishing to us and still remain a prisoner of the larger system. To truly escape, the speed must exceed the threshold for the galaxy, not merely the threshold for a smaller local structure. So yes, nature can fling stars outward through supernova events, cluster interactions, and black hole encounters. But only some of those stars become true exiles. Only some pass from dramatic motion into actual freedom. There is another way galaxies lose things too, and it is quieter in some ways, though just as profound. Galaxies interact with one another. They pass near one another. They tug on one another. Sometimes they collide and merge. Sometimes a small galaxy falls under the influence of a larger one and is gradually stretched, stripped, and absorbed. In those interactions, stars can be pulled from their original homes and cast into new regions of space. Some become part of streams, long rivers of stars tracing the tidal violence of past encounters. Some become members of a new merged system. And some may be thrown far enough, with enough energy, to leave a galaxy altogether. This is a beautiful and sad part of cosmic history. Galaxies are not isolated ornaments hanging untouched in darkness. They live in relation to one another. Their gravity reaches outward. Their past encounters leave marks. The sky we see now is the product of old meetings, old losses, old rearrangements of matter across unimaginable time. So when we ask whether anything can naturally escape a galaxy, the answer includes not just individual stars violently slung outward, but stars caught in the larger drama of galactic interaction. A dwarf galaxy, for instance, may orbit a much larger one and gradually be torn apart. Its stars may be spread into streams, absorbed into halos, or in rare cases flung so far that they no longer remain bound in the way they once were. The story of escape is not always one star meeting one black hole. Sometimes it is whole structures being reshaped by the gravity of larger structures. That should remind us of something else quietly important. Freedom from one galaxy does not always mean calm. Sometimes it is the result of catastrophe. A star drifting through intergalactic space might sound poetic, and it is, but the path that led it there may have involved disruption, violence, and the destruction of older gravitational relationships. Exile can be real and still not be gentle. There are also stars that may seem almost homeless in another sense, stars not obviously tied to any one luminous galaxy but found in the wider spaces of galaxy clusters. Some of these may have been stripped from galaxies through interactions over cosmic time. They still belong to larger gravitational environments, perhaps to a galaxy cluster rather than to a single galaxy, but they illustrate the same principle. Nature does not keep every star neatly inside the bright spiral or elliptical system where it formed. The universe is messier than that, more relational, more dynamic. Stars can be lost. Galaxies can leak. Gravity can rearrange its loyalties. That is one of the reasons astronomy is so moving. It is not only about stable things remaining stable forever. It is also about systems changing, merging, ejecting, breaking, and reforming over spans of time so large that even the word history begins to feel too small. And yet, despite all these escape routes and exceptions, the main truth remains untouched. Most things do not leave. That is what gives the exceptions their power. If every star could casually wander free, hypervelocity stars would not fascinate us. If galaxies constantly shed their members without effort, the very idea of galactic structure would be weaker. What makes the exceptions meaningful is the strength of the rule they break. The rule is belonging. The exception is exile. And nature, like all interesting systems, is defined by both. There is something else worth saying here, especially in the quiet tone of this story. When we hear about a star escaping a galaxy, it is tempting to imagine a clean departure, almost like a spacecraft achieving its mission. But that is not really what a natural galactic escape looks like. It is not usually planned, not orderly, not purposeful. A hypervelocity star does not choose its freedom. A stripped star does not decide to leave. These are consequences of forces far larger than intention. In that sense, natural escape is not adventure. It is aftermath. That may sound sad, but it also gives the phenomenon a kind of honesty. The universe is not staging dramatic departures for our emotional satisfaction. It is simply following the logic of mass, motion, and gravity. Sometimes that logic holds. Sometimes it ejects. And perhaps that is why escaped stars feel so haunting. They are not explorers. They are survivors of circumstance. A star flung from the Milky Way would continue shining for as long as its own life allows, carrying its light into a region with far fewer companions around it. It would not know loneliness. It would not reflect on what had been lost. But to us, imagining such a star, there is an undeniable loneliness in the image. A sun torn from its great stellar city, now moving through the darker spaces between galaxies. It is one of the most poetic realities astronomy offers. And it is real precisely because physics allows rare acts of release. There may be other kinds of natural escape too, depending on what object we mean. Gas can be blown from galaxies under certain extreme conditions. In some galaxies undergoing furious star formation, powerful winds driven by many supernovae can push material outward. Around active galactic nuclei, matter can also be accelerated dramatically. But gas is not the same as stars, and a cloud being driven outward is not quite the same story as a sun itself becoming unbound. Still, these outflows remind us that galaxies are not perfectly sealed worlds. Under the right conditions, they can lose matter. They can expel part of themselves. Even then, though, the deeper lesson is unchanged. Nature can achieve escape, but nature usually does so through extremes. And that has a quiet consequence for the question that sits behind all of this. If the galaxy only rarely allows stars to leave, and usually only through violent encounters or dramatic interactions, then that tells us something about what human technology is up against. It is not merely a matter of building a faster spacecraft. It is a matter of matching, in some engineered form, the kind of energy transfer that the universe itself only occasionally provides through its most severe events. That is a sobering thought. Black holes can fling stars free. Exploding stars can disrupt entire systems. Colliding galaxies can strip streams of suns into darkness. And even with all that violence available, most stars still remain bound. If the universe itself has to work that hard to produce a true galactic exile, then the galaxy's grip must be deeper than ordinary words like difficult can fully express. Still, there is comfort here too. Because these exceptions, rare as they are, make the universe feel alive in a broader way. Not alive like an organism, but alive with process. Alive with unexpected outcomes. Alive with histories so deep that even the loneliness of a star in intergalactic space becomes part of a larger cosmic pattern. It reminds us that galaxies are not closed boxes. They are participants in a wider drama. Their members can be born, moved, scattered, merged, and in rare cases, released. The Milky Way itself may contain stars that were born elsewhere and later joined it. It may have lost stars of its own to ancient interactions or violent slingshot events. The sky above us, calm as it looks, is part of a longer story of exchange and motion. Galaxies are stable, yes, but not frozen. They are persistent, but not sealed. That is a lovely balance. The structure is real enough to hold. The history is dynamic enough to change. And in the tension between those two truths, escape becomes possible without becoming ordinary. So can anything naturally escape a galaxy? Yes. Hypervelocity stars can. Some stars may be flung free through encounters with supermassive black holes or other intense gravitational interactions. Some may be stripped or scattered during galactic collisions and tidal encounters. Gas and other matter can sometimes be driven outward under extreme conditions. But these are exceptions, not the rule. The ordinary life of matter in a galaxy is not escape. It is orbit. It is membership. It is long participation in a gravitational home. Nature allows exile. It does not make exile easy. And perhaps that is exactly why this part of the story feels so satisfying. We do not end up in a universe where galaxies are perfect prisons. Nor do we end up in a universe where everything casually drifts apart. We end up somewhere more beautiful than either extreme. A universe where structure is strong, but not absolute. Where gravity holds deeply, but not always forever. Where rare paths lead outward, though the outward way is usually written in violence. There is something honest in that balance. And now, after all of this, the final question begins to gather itself. If galaxies can hold almost everything, and only rarely lose something through extraordinary events, then what does that tell us about the scale of the universe itself? What does it really mean, emotionally and physically, to say that leaving a galaxy is hard? What kind of reality are we living inside, if even a galaxy is just one structure among many? That is where the story finally widens. Because in the end, leaving a galaxy is not only a problem of speed or gravity. It is a lesson in scale. Part 10. Why leaving a galaxy is really a story about scale? By now, the idea of leaving a galaxy may feel less like a dream and more like a quiet impossibility. Not impossible in the strictest sense. Nature, in rare and violent ways, can sometimes fling stars free. Physics does allow escape. The universe is not completely sealed. And yet, after everything we have explored, the deeper feeling remains the same. A galaxy is not something you casually leave behind. It is not a neighborhood you walk out of. It is not even a country or a continent in any ordinary sense. It is a structure so vast, so heavy, and so patient that the very thought of escaping it forces the human mind into a different relationship with scale. And perhaps that is the real point of the entire question. Maybe the deepest lesson was never simply that galaxies are hard to escape. Maybe the deeper lesson is that we are not very good, at first, at understanding just how large reality really is. Because when people ask whether humans could ever leave the gravity of a galaxy, the question sounds like a travel question. It sounds like a matter of distance, engineering, and courage. It sounds as though the problem belongs to the same family as crossing an ocean, flying to the moon, or sending a probe beyond the planets. But it does not. Not really. At its core, leaving a galaxy is not just a problem of motion. It is a problem of perspective. It is a confrontation with size. If you enjoy these calm journeys through science and space, you can leave a quiet like, subscribe if you want more slow explorations like this, and share where you're listening from tonight. There is something comforting about the idea that while the galaxy holds all of us, so many different lives are listening from their own small corners of it at the same time. When we are children, the world feels large. A room is large. A house is large. A city is large. Then, with time, those scales begin to shrink under understanding. A city can be crossed. A country can be flown over. A planet can be mapped. The Earth itself, once mysterious and immeasurable, becomes something we can hold in images and globes and satellite views. Human knowledge has been full of this kind of shrinking. We make the world more graspable. We turn what once felt endless into something navigable. And because of that, it is very easy to carry the same emotional habit into astronomy. We hear about planets, stars, galaxies, and begin arranging them in our minds as larger and larger versions of places. Different in size, yes, but still belonging to the same general category of thing. A bigger place. A farther place. A harder place to reach. But the universe keeps resisting that simplification. A galaxy is not just a bigger map. It is a different order of reality. That matters because the mind can accidentally flatten enormous differences. We say Earth, solar system, galaxy, as if those were 3 steps on one ladder. And in a literal sense they are. But emotionally, the jumps between them are so severe that language can hide what is really happening. Leaving Earth is a technological challenge. Leaving the solar system is a civilizational challenge. Leaving a galaxy begins to feel like a challenge to the very way human intuition was built. That is why this subject lingers in the mind. It exposes how local our instincts really are. We evolved to judge the size of trees, rivers, storms, cliffs, shadows, distances that could once be walked or ridden or sailed. Even our greatest machines remain shaped by creatures whose original lives unfolded on one small planet. Our language for space still carries the memory of those origins. Far, near, beyond, edge. Those words are useful, but a galaxy stretches them until they become soft. The edge of a galaxy is not an edge like the edge of a forest. Far in a galaxy is not far like a faraway city. Beyond a galaxy is not beyond like the other side of a mountain. The words still work, technically, but they stop carrying the emotional weight of the reality they describe. And that is why the question becomes so valuable. Because it forces us to notice the mismatch. The difficulty of escaping a galaxy is not only a fact about gravity. It is a fact about the limits of ordinary imagination. One of the quietest shocks in astronomy is that the universe is not merely large. It is layered. Earth belongs to the solar system. The solar system belongs to the Milky Way. The Milky Way belongs to a small community of galaxies we call the local group. The local group belongs to still larger structures, threads and clusters in the vast cosmic web. And all of this exists within an expanding universe whose most distant regions are not simply far away, but receding under the growth of space itself. So even the phrase leaving the galaxy contains a hidden innocence. It sounds final. But nothing in the universe is final that way. To leave one structure is only to encounter another. To escape one gravitational home is not to arrive at some perfect freedom. It is to enter a wider environment, with its own distances, its own constraints, its own meanings of nearness and separation. That is one reason cosmic scale feels both beautiful and humbling. There is always another layer. Always a wider frame. Always a larger belonging waiting outside the smaller one. And yet, strangely, this does not make the universe feel colder to me. In some ways, it makes it feel more coherent. Because what we are seeing is not randomness. It is nested order. Matter gathers into stars. Stars gather into galaxies. Galaxies gather into larger systems. The same universe that produces emptiness also produces structure. The same darkness that can feel lonely also contains patterns of relation. The Milky Way is one expression of that order. Its gravity holds stars not because reality is cruel, but because reality is organized. Its depth is not a flaw. Its depth is what makes it a galaxy at all. This is worth resting with for a moment, because the language of escape can quietly distort the emotional truth. When we say it is hard to escape the Milky Way, it is easy to hear that as a limitation, almost as imprisonment. And in one sense, that word is understandable. We are bound to the system. We do not come and go freely. The galaxy's gravity is real. Its scale is severe. Its hold is powerful. But there is another way to see the same fact. What is difficult to leave is often what has truly held you. The very thing that makes escape hard is the thing that made a long, stable home possible in the first place. If the Milky Way were easy to leave, it would also be easier for its stars to scatter, easier for its structure to dissolve, easier for the conditions that created long-lived star systems, heavy elements, planets, and eventually life to break apart before complexity had time to deepen. The galaxy's grip is not only a barrier. It is also a gift. It is the reason the stars of the Milky Way are not just debris. It is the reason our sun has a galactic home to orbit within. It is the reason the material that became Earth had a wider environment stable enough to endure. In that sense, the difficulty of escape is a measure of how real the structure is. A galaxy that could not hold itself would not be a galaxy worth speaking of. This is where the whole question begins to turn from engineering back into philosophy. Because once you understand the scale involved, the emotional meaning changes. You stop asking only, could we leave, and begin asking, what does it mean that we are part of something so much larger than ourselves? What kind of creature looks up from one planet, in one ordinary arm of one galaxy, and wonders how to escape the full gravitational identity of its home? That is a very human question. Not because we are close to solving it, but because we are the kind of beings who ask it anyway. And maybe that is part of the beauty here. Human life is brief. Civilization is brief. Even the history of our species is brief compared with the age of the Milky Way. Our sun has been orbiting the galaxy for ages beyond written memory, and all of recorded history fits into a tiny fraction of that journey. The empires, languages, songs, cities, griefs, and victories of human life have all unfolded while our star has quietly continued its long path around the galactic center. We are brief, yes, but we are not irrelevant. Because in one corner of this galaxy, matter became capable of reflection. Stardust arranged itself into living things, and eventually into minds that could ask what gravity is, what dark matter may be, how galaxies hold themselves together, and whether freedom from them is possible. That is not a small thing. The scale of the universe does not erase that. If anything, it makes it more astonishing. A galaxy is enormous. But within one tiny part of it, there are beings who can think about the whole. There is something deeply calming in that idea. We often fear scale because we think it reduces us. We imagine that if the universe is too large, then our existence must become trivial. But scale can also work the other way. It can make awareness feel miraculous. It can make the ordinary act of looking up into the night feel like one of the most improbable achievements in nature. A galaxy is not only difficult to leave, it is also difficult to fully imagine. And yet here we are, imagining it anyway. Perhaps that is one reason these questions can be so soothing before sleep. They place us inside a story large enough to quiet many of the smaller stories that trouble us during the day. The mind spends so much time on local concerns, immediate worries, unfinished tasks, awkward memories, little loops of thought. And then astronomy opens a much wider window. It does not make daily life meaningless. It simply changes the scale at which meaning is being felt. Under galactic scale, some anxieties soften, some deadlines lose their sharpness, some restlessness gives way to awe. The same is true of ambition. Humans are ambitious creatures. We want to build, move, cross, solve, exceed. That drive has taken us from caves to cities, from fires to circuits, from boats to rockets. Ambition is part of what makes our species fascinating. But the galaxy reminds us that there are frontiers so large they cannot be conquered in the ordinary emotional style of conquest. They can only be respected. The Milky Way is one of those frontiers. You do not defeat a galaxy. You do not outgrow it with attitude. You do not reduce it to a motivational slogan. You study it. You marvel at it. You send small machines into its outskirts. You learn the rules it lives by. And in doing so, you gradually understand that the real reward was never dominance. It was orientation. To know where you are in the universe is already an extraordinary thing. To know that you live on a planet orbiting a star inside a barred spiral galaxy, itself moving within a larger cosmic structure, is already a kind of triumph. It is a triumph of attention, a triumph of patience, a triumph of minds slowly piecing together a reality they were never evolutionarily designed to grasp easily. And the story keeps becoming more beautiful the more honestly we tell it. Leaving a galaxy is hard not because the universe is mean, but because galaxies are vast. It is hard not because humans are weak, but because our intuitions were formed at the wrong scale. It is hard not because motion is impossible, but because freedom from deep structure is always more expensive than it first appears. It is hard because the Milky Way is real in the fullest physical sense. Real in mass. Real in motion. Real in history. Real in the way it holds us whether we think about it or not. There is another layer here too, perhaps the most peaceful one of all. We often speak about the galaxy as though it were separate from us, as though we were little strangers trapped inside it. But that is not quite true. We are not foreign objects dropped into the Milky Way from somewhere else. We are made of the same long history. The carbon in the body, the oxygen in the lungs, the iron in the blood, the calcium in the bones, all of it came from older stars. The matter that became us was shaped by the galaxy's own past. So when we ask whether we can leave the galaxy, there is a quiet paradox in the question. We are wondering whether a part of the Milky Way can escape the gravity of the Milky Way. Whether the galaxy, for a while arranged into us, can somehow step outside the larger form that made us possible. That does not make the question meaningless. It makes it more intimate. The wish to leave is being imagined by something that was born of the place it imagines leaving. And perhaps that is why the subject never feels purely technical. There is always something emotional beneath it. The galaxy is not just a destination problem. It is a home problem. To leave it would not simply be to travel outward. It would be to separate from one's deepest physical belonging. Maybe that is why the night sky can feel so familiar even when it is full of things beyond understanding. Some part of us recognizes that familiarity at a level below thought. The Milky Way is not just overhead. It is within us, in substance and ancestry. We are small, yes, but we are not separate. And that changes the meaning of scale one final time. Scale is not only about how tiny we are compared with the galaxy. It is also about how astonishing it is that the galaxy can, in some places, become self-aware through us. The large contains the small. The small reflects on the large. That is one of the gentlest miracles in science. So if we gather everything we have learned, the answer becomes something like this. Escaping the gravity of a galaxy is so difficult because a galaxy is one of the deepest, most massive, most persistent structures most of us can meaningfully talk about. It holds stars in motion for billions of years. It contains visible matter and hidden matter. It extends beyond what the eye first sees. It is not a simple object with a neat edge, but a vast gravitational environment. And we are not near the edge of that environment in any practical sense. We are inside it, moving with it, built from it. That is the physical answer. But there is also the emotional answer. Leaving a galaxy is hard because the universe is larger than human instinct likes to admit. Because reality keeps extending beyond our first picture of it. Because the very structures that make life possible are often the same structures that make freedom more difficult than we imagined. Because scale is not just a number. It is a way the universe teaches humility. And humility, in the best sense, is not humiliation. It is clarity. It is the calm recognition that we live inside something magnificent. Maybe that is the most satisfying place to end. Not with defeat. Not with the claim that we will never do this or that forever. Science is too alive for those kinds of final declarations. Human imagination is too alive as well. Perhaps one day our descendants, or descendants of our machines, will move through the galaxy in ways we can barely picture now. Perhaps our relationship to distance will change. Perhaps what feels impossible tonight will become discussable in some future age. But even if that happens, the lesson of scale will remain. The galaxy will still be immense. The Milky Way will still be a structure of astonishing depth and beauty. And the fact that it is hard to leave will still be one of the clearest signs that it is real. So when you look up at the Milky Way, or even just imagine it now as you drift towards sleep, maybe there is no need to think of it as a prison at all. Think of it as a vast architecture of belonging. Think of it as the long gravitational home that held the stars long enough for one of them to host a planet like Earth. Think of it as the reason the night sky has order. Think of it as the larger body from which our own brief lives were formed. And think, too, of how extraordinary it is that within this immense, difficult-to-leave structure, something as small as a human mind can still ask questions large enough to reach its edges. If this slow journey helped you unwind tonight, you can subscribe for more quiet explorations like this, leave a gentle like, and share what part of the universe you'd want to hear about next. For now, rest a little. The galaxy is still turning. The stars are still moving. And for this small, quiet moment, you are home inside it.